Hi, it's time for another math easy solution, and today I'm going to go over further into vectors and the geometry of space, and this time look at problems plus, which is a series of advanced math problems at the end of the chapter in my calculus book. Alright, so let's continue further, and note as always, if you don't have time to watch the whole video, you could play this video at a faster speed. Top secret life hack, your brain gets used to faster speed. You could also download and read the notes, or read the notes in article format on the Hive blockchain. You could also watch the video in parts, and timestamps of all parts are in the description, as well as the video sections playlist, and as well as links to everything here. And the video sections playlist will include basically short clips of this entire video, and I'll be uploading those shortly after this video. And again, links to everything in the description below. Alright, now let's take a look at the calculus book reference that I use. So note that I mainly follow along the book Calculus Early Transcendental 7th edition by James Stewart. And also note in some earlier videos I use the 6th edition. Alright, let's continue further. So calculus book chapter. So the Hive notes and sections playlist for each video of this chapter are listed below. And here is all of them right here. So this is a link to this is the main playlist right here, vectors in the geometry of space. And then each part of these has, this is the video notes on the Hive blockchain's 3D coordinate systems. And there's the playlist right here, and this play button on YouTube right there. And I have them all over here. And so this is the last part of this chapter, vectors and the geometry of space, and that's on problems plus, which we'll be doing, and so on. Also, note these links are also on MES links right there, mes.fm/links. You can go there. There's a math tutorials. I have the infinite sequence and series, similar setup, and I'll be uploading all those, and also for basically all the videos that I've done, I'll be working on getting those all out as well. So you can go there and see all the links to them there. Alright, let's continue further. So now let's look at the topics to cover. Note that the timestamps will be included in the video description for each topic listed below. And yeah, in this problem we're going to have, or in this video we're going to have 8 problems, and you can see them all right here. And I'll be going over them one by one. Alright, now let's take a look at the first problem, and this is problem 1, tightly packed balls in a box. Oh, I gave that title there. So each edge of a cubical box has length 1 meter. The box contains 9 spherical balls with the same radius r, and the center of one ball is at the center of the cube, and it touches the other 8 balls. Each of the other 8 balls touch 3 sides of the box. Yeah, so thus the balls are tightly packed in the box as in the figure below. So each one of these ones touch this line, or this side, and this top one, and the other side there, for example, this one here. So each one touches 3, and so on. So there's basically tightly packed 9 tightly packed balls right here with 1 in the center. Like that. And the box is 1 meter, each side is 1 meter. And the question is asked, find r. So in other words, what's the radius of this ball? So every one of these balls has the exact same radius, and so on. So what is r if you have 9 packed like that inside? Alright, so let's take a look at the solution. Actually, before we get to the solution, we're actually given a hint from our calculus book. So hint says, if you have trouble with this problem, read about the problem-solving strategy called use analogy. And I'll put a here like that. Read about this problem solving one, and this is actually from an earlier video or an earlier chapter, but I didn't actually make a video specifically on it, but I'm just going to read what the that section of the calculus book said. So use analogy. Try to think of an analogous problem that is a similar problem, a related problem, but one that is easier than the original problem. If you can solve the simpler problem, then it might give you the clues you need to solve the original, more difficult problem. For instance, if a problem involves very large numbers, you could first try a similar problem with smaller numbers. Or in our case, this one's going to be helpful. If the problem involves 3-dimensional geometry, you could look for a similar problem in 2-dimensional geometry. Or if the problem starts with a general one, you could first try a special case. So in our case, we're going to use we'll look at a 2-dimensional problem first. So here it is. This one's 3D. It's all complex. But we'll look at a two-dimensional, basically analogous case. So solution: solving the 2D case first. So since three-dimensional situations are often difficult to visualize and work with, let us first try to find an analogous problem in 2 dimensions. And the analog of a cube is a square, and the analog of a sphere is a circle. Thus, a similar problem in 2 dimensions is the following. And this one is, it states, if 5 circles with the same radius r are contained in a square of side 1 meter, so that the circles touch each other, and 4 of the circles touch 2 sides of the square, find r. In other words, we're just going to have, imagine you just have a 2D version like this. So you'll have one in the center, and then one like here. This one touches 2 sides, one and right here and there, and this one, and they all touch each other. I'm just drawing it really bad. This one goes like this, and I think it goes like that. No, actually, it is right. These all touch the sides and each other, but not these ones do not touch. So there's a difference there, and this goes like this, etc. So again, very analogous to the 3D case right here. So again, there's a separation from here. The center one does in between here doesn't touch here, but they all touch at the spot over there. All right, so that's how it looks like there. All right, and here I quickly just pause the video and just fix this. I just drew these out better, just using just built-in shape creator thingy in OneNote. All right, so that's how it looks like, and yeah, these all touch the sides again. Close enough. All right, so going further, so to solve this, we need to solve for r. So basically, we want to solve for r like that, for example. All right, so I'm gonna leave it like that. So the diagonal of the square can be determined by the Pythagorean theorem. So we know the sides are 1, so we could solve it out. So we know that the sides of the overall square is 1, 1, 1, 1. So we can go Pythagorean theorem right here and solve C, and recall that C is just, well, C squared equals to A squared plus B squared. In other words, we're going to get C is equal to plus or minus, and we just take the plus. I always do plus or minus just because inside could be negative as well. It's a very interesting concept. Anyway, so the sides are 1. 1 squared plus 1 squared equals 2. Well, square root 1 plus 1 is 2. Like that. So the diagonal is square root 2. So we're going to need this for our finding our r. Alright, so now going further, so let's write the diagonal of a square as a function of r and x, where x is the diagonal of is the diagonal square. No, I mean where x is the diagonal of a smaller square of side r, and solve for r. Yeah, so in other words, we have something like this. I just copied it from the solutions manual. Yeah, basically you have these 3. So if you look at a diagonal, so you have the radius here, r, 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 r. So there's 4 r's, but now we're going to have this square. So let's say we draw it on this side as well. So we'll have x side like here. These are x. X is the diagonal. So this is radius r, r, and then there's x is the diagonal like that. So then the diagonal of the overall diagonal, this equals to square root 2, which we had written over here. Square root 2, this is going to equal to, well, 4r plus 2x. And we know x is a diagonal where the sides are r, so we can just use Pythagorean theorem as well. So then this is all going to be, let's put these all together. Basically, we're going to get I'll put it separately. So x is equal to, well, again, plus or minus, we'll take the plus, square root, and then it's going to be r squared plus r squared, which equals 2. This is going to be just square root 2, and then, square root 2 r squared, which equals to square root 2 r, like that. Yeah, so that is the x value there. So I'll box this, and we're going to throw that inside. What we're going to end up having is the overall square root 2 is equal to 4r plus square root 2r. Alright, so that's if we factor out the r and move it on this side, is r going to be, well, 4 plus square root 2 equals to square root 2. So put this all together, r is equal to square root 2, you guys divide it out, 4 plus square root 2. So there is our r value. Alright, so now that we've solved the 3D case, the 2D case, so now we could solve the 3D case. So this one, let's use these ideas to solve the original 3-dimensional problem. So the first thing that we need to do is find a diagonal. So the diagonal of the cube can be determined using the distance formula in 3D. So again, from my earlier video right here, So the distance formula we have, so the distance P1, P2 between the points, P1 and P2 in 3D is equal to basically the same thing as the Pythagorean theorem, but it's in 3D now. So the difference of these coordinates, then squared, and then so on. So x, then we'll have the x1 squared, the y's, and the z squared on all square root. And in our case, what I'm going to do is I'm going to just draw the cube. Say we have a cube like this. So this is our cube. Okay, and we'll just do coordinates quickly. So let's say this is the z axis there, and it goes like this all the way to the origin. So let's see the origin's there. What I'm going to do is go all the way across here. This is the x, and then this is the y. It goes across there, and we're going to go point from this part all the way over to here. So all the way from there to there. This is the origin is 0, 0, 0. So again, in our case, the x1s all just vanish as 0. So 0, 0. And then this part right here, in our case, all the sides are 1. So 1, 1, 1. So then this right here is going to be 1, 1, 1. So in other words, our diagonal, I'll just put D. So this right here, D is equal to square root. Again, it's just going to be 1 squared. So 1 minus 0, squared 1 plus, 1 minus 0 is 1. So for every single one, 1 squared plus 1 squared plus 1 squared equals to square root 3. So that is our diagonal. Instead of square root 2, we have square root 3, which is quite interesting. Alright, so similarly, let's write the diagonal of a cube as a function of r and x, where x is the diagonal of a smaller cube. Again, instead of a square, we're doing a cube with edge r, and then we're going to solve for r. So in our case, here, let's just draw our cube in 3D, like that. So there's our cube. So draw it a bit better. So this is our cube like that, make it fit in a bit better. Okay, so there is our cube, so something like this. And this goes like that, and line up these together. So there's our cube. Alright, so that's the cube, and I'm going to draw in red our balls, or spheres, small spheres like that. So I'm going to draw it, it's a bit hard to, well, we just need 3 of them. I'm going to go diagonal from this corner all the way to this right here. So we're going to have, I'm going to draw a big one like that, and another one like that. And then one all the way like this. Okay, so we have like that. I'll make it try to make them all the same size. Alright, so I have drawn them like this, so that's good enough. And now what we're going to do is I'm going to draw in blue our distances. So from here to here, this is our r. We also have another r like that. Then we also have another one here. So we have r, 3 r's, and there's also one here. That's also our r. So we have 4 r's, again, same thing as before. Yeah, but now we're going to have a cube here. So we're thinking this in 3D. This is the diagonal of a smaller cube with sides r. So we're going to go from this point like that. Then we're going to draw it like this. Then down. This lines up like that. And this goes across like that. So just think of it as a cube there. And here I just fixed that up. So again, all the sides are going to be r, r. It's all the same radius there, r everywhere. And then now we have a diagonal. It goes across this to there, and that's going to be our x. And I'll draw that actually a different color so it's more visible there. We'll go this one in green. All right, so green is going to go across to there, and that's our x. All right, so that's our x. So now we could just get back into the same exact, we're going to have the exactly the same formula. So the full diagonal, so I'll call it D, this equals to cube root 3. This equals to, this equals to 4. Yeah, it's going to be 1, 2, 3, 4. And there's also another point like here. This is going to be also x, like that, x. So it's going to be equals to 4r, so 1, 2, 3, 4, and then plus 2x. 2x. And where again, x is just the diagonal, this equals to square root, and then this is going to be in 3D now, r squared plus r squared. It's a diagonal of the cube instead of the square, like that. So we're going to have square root 3 now, and then r like that. So that is our x. Alright, so if we put this all together, we need more room. We'll move it over here. So d equals to square root 3, and then equals to 4r plus 2x, which equals 2, and this is going to be 4r plus the 2x is going to become, well, again, it's square root. It's going to be 2 times square root 3, and then r, square root 3r. Alright, so that's what we have there. Now we can just factor out the r. So we're going to have, and move it over to here. So r is going to be 4 plus 2 square root 3, and this equals to square root 3 like that. So this means that r is equal to square root 3 over 4 plus 2 square root 3. Alright, so we could stick with this right here, but my calculus book actually continues further and simplifies it further by multiplying it. I believe it's called the conjugate. So the bottom right here, instead of so multiply the top and bottom by the denominator, but with a negative. So we'll have some bunch of canceling out stuff. So 4 minus 2 square root 3 like that. So it's basically the idea is just only have one square root as opposed to 2, and also make it at the top as opposed to the bottom. So this equals 2. This is going to be 4 square root 3. Minus 2 times square root 3, this is just going to be 3. Over, so 4 times 4, so just to FOIL it out, 4 times 4 is 16. Yeah, so this is going to be, I'll just keep it as squares. 4 times 4 is 4 squared, and then 4 times 2, yeah, it's going to be 8 square root 3. And now multiply this by, this one here is going to be positive 8 square root 3, and then the last one, multiply these together, is going to be 4, and then 3 times, yeah, square root 3 times square root 3 is just going to be 3, like that. So then extend this out, this cancels, and we're going to be left with, this is 16 minus 12, this equals 2, and this part right here is just going to be 4 square root 3 minus 6, and this is going to be, yeah, this is going to be 16 minus 12 equals to 4. So 4 square root 3 minus 6 over 4, and divide this out by 2, and we're going to get a, this is going to be a 2, 3, 2, and then also divide this all out. This is going to be, where are you going to go? I'll put it up afterwards. So square root 3, or 2 square root 3, and then minus, yeah, all those do 2 square root 3, over 3 over 2, and then you can also, again, simplify it even further. And this equals, just divide it out, it's going to be square root 3 minus 3 over 2. Alright, so that is our radius. So again, you can simplify it, these are the exact same thing. Square root 3 over 4 plus 2 times square root 3, or simplified to square root 3 minus 3 over 2. Amazing stuff. And this is in meters, so I'll put a bracket like that, and I'll put meters like that. So, meters. Alright, now let's move on and look at problem 2. And this one is finding the volume around a solid box. So it's not volume of a solid box, but around one, as we'll go over here. So let B be a solid box with length L, width W, and height H. Let S be the set of all points that are a distance at most 1 from some point on B. And then we're asked, express the volume of S in terms of L, W, and H. Alright, yeah, so there's basically a box, and then the volume that is just a shape around it, but it also includes that box, as we'll go to it further. And now let's look at the solution, and to better grasp this, we're going to use similar technique in the as in problem 1. We're going to use the problem-solving technique of using an analogy. So solution: solve the 2D case first. So let's try an analogous problem in 2 dimensions first. And then we'll see what we need to do for the 3D case. So consider a rectangle with length L and width W, and find the area of S in terms of L and W. So this would here, let's say, yeah, this would be a rectangle right here. So this I just copy and paste from my calculus book, just easier to work with right now. And now we're asked for the shape around it. It's going to be at most 1 from any point on the box. and the furthest point on that rectangle is going to be over here. So then at distance 1 is like that. And then at the edges, the furthest distance is going to be like this. That's 1. And then as you can see, you're going to form a quarter circle. So a curved shape like that. That's actually a quarter circle. This is a quarter circle. So you're going to have a full circle there, length 1. And yeah, so let's find the area of this shape S. And this area actually is the entire area, and it includes the rectangle. All right, so let's write this down. So I'm going to write A of S. So this equals to, well, it equals to this first. So it equals to that. That's going to be LW, just a rectangle, plus the next shape. So that we, yeah, I'll keep this highlighted. Okay, plus the next one is going to be, well, this right here, and this. And that's just going to be, well, 2 times by the length, the width of this one's 1, the length is L there. So we're going to go L times 1, like that. All right, so the next one is we're going to have this and this. And that is just 1 times W, but there's 2 of them. So 2W times 1, like that. And then the next one is this right here. Yeah, this. Yeah, I'll just write this a bit better. Do that, this, and this. And so that's a quarter circle. Yeah, so this is going to be 4 plus, well, quarter circle is going to be, yeah, plus 4 times by a quarter circle. So quarter circle will be 1/4, and then the area of a circle is pi r squared. So pi 1 squared, like that. And I'll just draw this here better. So this right here is just going to be 1/4 of a circle. So this is going to be of a circle. So in other words, I'll just draw this better. This is, if you have a circle like that, so this is going to be 1/4 of it, like that. So that's 1/4 circle. And that's yeah. Again, look at this shape right here. This you combine them all together, you form a perfect circle. So then this simplifies to, this just becomes LW plus 2L plus 2W plus, and then the 4's cancel. We're just going to be left with plus pi, like that. This is our area of the shape S right here, which includes the full rectangle. Alright, now that we've gotten a 2D case, now this can help us solve the 3D case. So now in 3 dimensions, the volume of S is, so let's draw this out first. So let's draw our solid box first. So we have a solid box, and now we have to include the factor for the height. So there's the height H, there's the length, like that, is L. So this is the length L. And then it has a width W, so you have a width right here, W, and I'll draw this W, so keep it there. It's W like that, and it goes like that. So there is our, so there's our box. So what I'm going to do right now is we're going to write the volume of this box, of the full S, and part. So the first one we have drawn already. This is just going to be length times height times, or length times width times height. Alright, so we have that. So then we're going to add, the next section is again, distance 1 from it. So let's draw this in a different color, and let's pick red right here. Alright, so we have red, and what we'll do is, let's take the top part. The part's going to look like this. Say we have a length 1 like that, and this goes like this. And there's going to be actually 2 of them. Yeah, let's draw this a bit better like that, and this goes across like that. So that is that, and this has length as, or the height is 1 of this one, but there's going to be 2 of them. So what I'm going to do is move this down right here, down a bit more. So this is going to be like this, like this, like that. All right, so we have like that. And this also has the height 1, and again has the width W. So we're going to have 2 of them. So what I'll do is, well, I'll keep it in red actually, just to, so it's pretty interesting like that. So 2 times, we're going to have length times it by W times it by 1. So LW1. Let's keep it like that. LW and then 1. And I'll put the dot like that. Okay, just keep it the dot there. Just for the 1, like that, and I'll keep it all there, just because we usually don't, 1 numbers and letters together. They're not usually written together unless it's there's a multiplication there. Anyway, so LW times L times W times 1, and now the next one we're going to draw this in blue. So let's say we have a blue right here. And we're going to go with this side. Actually, we're going to go, yeah, I'm going to draw in front of us. Like this. Oh, it's going to be 3D, so I will draw it like this. Yeah, it's protruding out this way, and then it's like that. And so on. Like this. Okay, let's fix this up. Like this, and then it's protruding out by 1, and it has a height h and LW, and there's 2 of them. So we have always on the other side as well. I'll just keep it like that. I'll just draw it like that. Anyway, so there's 2 of those. This is going to be plus 2. So plus 2 times, and now we're going to have length L, height h, and then times it by, this is the protruding, the width 1. Alright, so the next one I'm going to draw it actually in green. We're going to get, again, now it's going to be protruding out this way. So we have something like this. And there's a section out like that. And this is protruding out by 1 there. And this one has width and height. So we're going to have 2 times width, height, and then times by 1, like that. And let's draw the other part out as well. It's going to be out on this side there. Like that. Alright, so again, it's all convoluted, but you get the idea. Alright, and now we're running out of color, so I'm just going to use black for the rest. Now we're going to have an interesting sections right here. So we're going to have actually a cylinder or a quarter cylinder like this that goes across there, has length or has radius 1, 1, 1, like that, and has width W. And there's going to be, well, there's going to be actually, let's go one of these, and it's actually going to be at the bottom as well. So it's going to be like that, and it's at the bottom, so we actually have 4 of these. So in other words, we're going to have plus 4, and what I'm just going to do is times it by, we're just going to have 4 cylinders, a quarter cylinders like this. This is going to be, this is going to be height and width 1. I mean, width like that, height and depth or whatever is 1 like that. So 4 times cylinders like that. And then we're going to have another 4 over here, so like this. And this, again, it's all convoluted, but if you're following slowly, you can grasp it. Alright, so there's 4, and then in the back as well, somewhere in the back like that as well. Let's see, it's all, yeah, it's very, very convoluted. And I put it in dash line, so it's going backwards. Find it. Alright, so that's going to be now 4 times it by. And this one is, yeah, this is going to be 1, 1, and then this is, actually, no, that one we already drew that. I mean, it's going to be over on this side right here, I mean. So the top here and here, and on the back side as well. So we have the back side already. And that back side, yeah, this is going to be length L, and there's the 1, 1 there. So this is, yeah, so height, depth, or width, whatever, 1. And then there's the L there. So it's going to be 4 times. I'm going to draw it like this. 1, 1. And it goes all the way across. And it's the long one. Like that. This is going to be L. Like that. All right. And now there's even more. We're going to have actually now 4 these ones now. So if you look at these green ones. So green connects to the... I'll move it around this right here. Yeah, green connects like this. So it loops like that. So cylinder... around here and here, and here and there, and around it. So this is this part and around like that. It's a bit hard to see here. Let's draw this in 3D. Like that. That's going to be around it. So anyways, so that's going to be 4 of those, and I'll make a dash line as well here underneath there. So that's 4 of those, where it's going to be, yeah, the height of that is h. So we'll draw it like this, 4 times. Like this, and then it's a curve here. It's 1, 1, and now it's the height is h, like that. And then lastly, now if we look at the corner, there's actually 8 corners. So 8 corners, 1, 2, 3, 4, 5, 6, 7, 8. So 8 corners, and in this part right here, what we actually have, and it's hard to see, it's going to be at the corner. We actually have, and again, it's a curved shape. The distance all is 1. From the central spot like that, and has 3 flat sides, 1, 2, and 3, And in fact, I think it's already pretty much drawn inside in here. I'm just going to shade this in. This is actually 1/8 of a sphere. So what we'll do is, if I look at this right here, and again, if you remove all the centerpieces and combine them together, you're going to get a perfect sphere, similar to how we had a perfect circle right here. So instead of 1/4, now we're going to have 8. There's 4 corners there. I mean, there's eight corners because of this box. And so what we end up having is this is going to be, if I draw this in 3D, it's going to look like this, and this, like that, and this is going to be, one, like that, and then I'll draw this fully. This is the full diameter across like this, and then the full height, or around there, the whole thing around there. So it's basically a full sphere. I think it looks something, it looks something like that. This actually ends up going here, like this. I think something like that. And where this is the full sphere. So we have 1/8 of a sphere. Again, it's hard to see exactly, but yeah, that's what it is. And you could use your imaginations there. And again, there's 1/8 of that sphere there. So epic stuff there. All right, here, just fixed that up. Made some solid piece on the solid lines on the around side. Anyway, so that's a quarter there. So now we can just put these all together. We're going to get equals 2 LWH plus 2LW plus 2LH plus, and then we're going to get actually, instead of the 2, we're going to take out the 2's everywhere. Plus 2, so remove the 2 out of those. Actually, we'll do that afterwards. So LW plus 2, just put everything in first, then we're going to simplify it. So 2LH, now then 2WH, and then next part right here is going to be plus 4, and that's a cylinder, and the cylinder has, this is just 4 of those. In other words, 4 times a quarter cylinder. In other words, we just have a full cylinder, and this is radius is 1. So the area, basically, it's going to be the area of a circle times it by the length. So in other words, we're going to have pi 1 squared divided by times by w. And so in 4, basically 4 of those basically becomes one cylinder. And the next one right here is going to be plus 4 times this one here. Again, we can ignore the 4 and just consider a full cylinder. So pi r squared, so pi 1 squared times it by L, like that. And then the next one here, similar to here, remove the 4, and we're just going to get pi 1 squared, the area times by the height, and like that. And then the next one here is 8. Again, there's 8 of this, so 1/8 of a sphere just becomes a full sphere. And recall the equation of a volume of a sphere, just 4/3 pi times 1 cubed. Yeah, so that's r cubed. So then simplify this all. Yeah, simplify this all. We get right here v over s. V of s or the volume of the full shape is equal to LWH plus, and then factor of the 2, LW plus LH plus WH. And then plus, this is going to be pi, and we can also factor out the pi out of everything. Yeah, so we can factor out the pi out of the W, plus the L, plus the H, and then plus, and I'll just move this all the way here, plus 4/3 pi. Alright, and now we can just box this whole thing in. So there it is. And note also, again, this is from my earlier video, note the equation of a sphere is 4/3 pi r cubed. Alright, now let's continue on to problem 3, and this is looking at intersecting planes. So let L be the line of intersection of the planes, and then it has cx plus y plus z equals c. And x minus cy plus cz equals -1, where c is a real number. And then in part A, we're asked, find the symmetric equations for L. And then part B states, as the number c varies, the line L sweeps out a surface S. And we're asked, find an equation for the curve of intersection of S with the horizontal plane z equals t, the trace of z in the plane z equals t. And then part C states, find the volume of the solid bounded by S and the planes z equals 0 and z equals 1. Alright, so this is a very complex question just to figure out what's even happening here. But if we go slowly, it all starts to make sense. So let's take a look at the solution to A. So A, we're asked to find the symmetric equations for L, the line of intersection of these two planes. And we could find the line of intersection L as in my earlier example. And here's a link to my earlier video on that. You could watch that. And basically, the first thing we'll do is first observe that the point -1, C and C lies on both planes. So when you have a point that's on the intersection, then we could find that line and so on. Yeah, basically, if it's on both planes, in other words, it's on that intersecting line. So what we'll do here is let's write the first equation. So cx plus y plus z equals c. So cx plus y plus z equals to c. And then if we write the second equation, x minus cy plus cz equals -1. So x, and then this is going to be minus cy, and then plus cz equals to -1. Let's double check that. Yeah, negative cy, cz, -1, and so on. So that's correct there. And what we could do is, well, we want to get rid of some of these, so we can subtract both of these. But first, what I'll do is I'm going to multiply c by the entire equation on the bottom here, and then subtract the entire thing here. So we're going to subtract c minus c on all this. So we just do some equation algebra right here. So we're going to subtract them all. So cx minus cx right here is going to cancel to 0. Then y minus right here, and so I'll just write that y minus c times cy, that's going to be, the negative becomes a positive, so plus c squared y. And then the next one's going to be plus z minus, now we're going to have a c squared z, like that. And then equals to c minus, and the negative, so it's c plus c. And yeah, get rid of the squared. Yeah, my mistake there. So it's a z, not a c squared, not z squared. So now what we're going to get is I'm going to factor out the c right here. C squared out, we're going to have a y minus a z. So basically this and this. And then the next one's going to be plus y plus z equals to 2c. Alright, so now in this case here, if we want to vanish this right here, so let's take a case right here. If right here, if y equals to z, then we're going to have a c squared, let's go, it's going to be y minus, let's get, y is just going to vanish like that. And then I'll just put it as y, so this vanishes to 0, and this is going to be, again, plus y, I'll put it as y, so you can just replace them together, equals to 2c. In other words, we're going to have a 2y equals to 2c, so in other words, y equals to c equals to z. Like that. Because basically we had if y equals z, and then we could plug that inside the first equation. So let's go 1 right here. So any equation. So the 1 right here, and we're going to have c x to solve for y. So plus y is c, plus c like that, plus, and then z is c. Plus c equals to c. This cancels, and we're just going to be left with right here, cx, move this over to the other side, equals to negative c. In other words, the c's cancel, x equals to -1. Like that. Yeah, so thus we get the point on both planes, and hence the intersection point is going to be -1 and c, like that. Alright, so now we have a point on both planes, and hence the line of intersection. That's a -1, c, and c. And now another thing to note is we know that if you have, these are the equations of planes, and the equations of their normal vectors are included inside these equations. So put a note right here. So recall also that the normal vectors of each plane is included in their linear equations as per my earlier video, and here's a thumbnail of that video. So equation of the plane, so the dot product is a normal vector perpendicular to the plane, dot product with r minus r naught vector like this. That's a point on the plane, just the 2 points on the plane, subtract it, and then you're going to have it like that. And then to dot product equals 0, you get this linear equation when you expand it out, and so on. And then the normal vector right here is this A, B, and C. So those are included in this normal vector right here. This equals to A, B, and C normal vectors. So let's just obtain those because we're going to need them. Yeah. So thus for our equations, we have Cx, the two equations plus Z plus Y plus Z equals to C, and again that's this right here. Cx plus Y plus Z equals C. The next one is X minus Cy plus Cz equals -1. X, and then this is going to be minus Cy plus Cz equals to -1. Yeah, so that's the normal vectors. I'm just going to write this as normal vector 1, and 1 of this one is included in there. That's just going to be C. Again, it's just in front of the 1. So Ax plus By plus Cz. In other words, we have right here, yeah, so we have the normal vector of the first plane, C, 1, and 1. And then the next one, and 2, this equals to, let's make this a better line, like this. And this equals to -C, C, and actually no, there's a 1 in front, for the 1 for the Z, for the X. 1, -C, and C, like that. Alright, so we have these two normal vectors. I'm going to box these out. We're going to need them. Alright, so going further, so now since L lies in both planes, it is perpendicular to both the normal vectors n1 and n2, thus parallel to their cross product. And I will illustrate that soon. So recall the cross product right here is basically if you have two vectors, A and B, separated by an angle, the cross product A cross B is perpendicular to both. And yeah, it goes like that. And there's a right-hand rule for this is for the angle, curls in like that. And the cross product is written in determined form right here, and you could obtain, basically it's going to be this, and then you can obtain the cross product and so on by crossing out some stuff. So for example, this one right here, cross out this A times, A2, B3, and then minus A3, B2, and so on. And we'll do that as we go further in. Yeah, again, if you haven't just grasped on it, there's the formula there, and I'll show you the shorthand as we solve it. And just to illustrate this, so since L lies in both planes, so again, we have the two planes are intersecting, and we already solved the point that is on both. So let's say we had a plane like this. Let's say this is plane 1. This is, let's just say this is the plane 1. This is a line of intersection. Let's say it crosses like that. There's a line of intersection. I'll draw the line first, actually. Let's say we had a line of intersection like that, and we had a plane like this, and it's intersecting right on this line, but there's two planes right here. There's another one like here, crossing this, and it goes behind it. So it goes like behind it, this one goes below it, and so on. So there's two planes, and there's a line of intersection L, like that. And then on, let's say this is the first plane. Let's say the perpendicular vector to it. What I'm doing is I'm going to draw it like this, and it's perpendicular to this one. So it's perpendicular to that, like that. And this is going to be called N1. And let's say we had another point right here on this one. Now perpendicular on this one here is going to be somewhere across, let's say it looks like this. This is, I'll draw it a bit further out. I'll just draw it actually here. Just to hide it away. So like that. And let's say this is perpendicular to this there. Like this. And this is N2. And then when you take the cross product of both of these, again, you could just shift these, superimpose onto itself. You're going to get again, using right-hand rule, that's going to be either up or down, but perpendicular to both. So this is going to be N3. I'll just go like this. I'll just put the N3 right here. So this is going to be perpendicular to both and is be parallel to the line. So this is going to be like this, N3, like that. Yeah, so in other words, read that again. So now since L lies in both planes, it is perpendicular to both the normal vectors N1 and N2, thus parallel to their cross product. So then this is, this is going to be parallel to the cross product of these two right there. So we just solve for the cross product, and then we obtain the parallel vector, which is again a direction vector, and we could solve for the symmetric lines. So N3, let's solve for the cross product, equals to cross of N1 cross N2, and again, it doesn't matter which one you do first or the other one, you're just going to get a reverse negative or positive, but this along the same parallel segment there. So it's going to be like this, and I'll shift this over down a bit, and it's going to be I, J, K components. I, J, and K are the X, Y, Z components like that. So that's that, and then the parallel vectors we had. I mean the normal vectors C11. That's it. C11, and then 1 negative C C. 1 negative C. Yeah, C like that, and just cross it out. So basically, now we could just solve for this, and then using the shorthand, you cross this out, cross the first segment there, and now we're going to multiply this by this, and subtract it by this, like that. So we're gonna get right here 1 times C is C, minus, and be a negative right here becomes positive, and minus 1 times negative C. So minus a negative C is going to be C like that, plus this is the I like that component. Erase this, do the same thing over with here, and now this part here is going to be a minus, because remember the cross product, it's going to be a minus, then the next one's plus, and we do the same thing. Cross it out. We're going to go now C times by C right here. C squared minus 1 times 1 is 1, like that. And then this is going to be our ij. And then plus, now the k1, erase this, cross this out. So now we're going to go C times negative C is equal to negative C squared, then 1 times minus 1 times 1 is 1. Like that, k. Like that. Let's erase this out. And write this all down. I just write this in component form or in the vector bracket form like that. C plus C is 2C. And then we're going to get negative C squared plus 1. And then this one's going to be negative C squared minus 1, like that. So this is our n vector, or n3 vector. And again, this vector is perpendicular to the normal vectors of the planes, but it's parallel to the line itself. So that's going to be used as our direction vector. Yeah, so thus we can obtain the symmetric equations of L. And there's a link to my earlier video as a thumbnail. So if you have direction vector, so there's the line right here, L, and then this equation in vector form equals to R. So vector pointing to a point on the line L, equals to a vector pointing to a point on L, and then plus t, just a parameter t, times it by a parallel vector or direction vector. So v like that. So that's parallel to it. So that's parallel to it like that. Yeah, I should have put a line like that parallel to it like that. So that's that. But anyways, that's straightforward. So that, and this one is going to be A, B, C like that. And then the symmetric equations is just going to be, you take the components of these, add these up right there. So x naught plus t times A. And then y equals y naught plus b times t. Then and same for the z. Then if you equate this as solve for t's, move this over to the other side, divide by b. So you're going to get this, and then equate all the t's. And then again, you're going to get these symmetric lines, symmetric equations of the line, and then you equate all the t, so you get rid of the parameter t, and you get these like that. Yeah, so in our case, we have, let's say our line L, it has a direction vector, like here, that's a parallel vector. This equals 2, and this is going to be our n3. This just equals 2. I'll put this n3 like that, in our case, and this equals 2c minus c squared plus 1. And then that's the next one, and then minus c squared minus 1, like that. And then the next part we need is just the x naught, y naught, z naught. Again, that's just a point on the line, and we already know a point on the line, and that's over here, point negative 1, c, and c. So our p naught, this part right here, so p naught equals to negative 1, c, and c. So we have everything to make the symmetric lines. Yeah, so thus we have the symmetric lines. This becomes, we're going to have x minus x naught. This would be negative 1 minus negative 1 to be plus 1. Divided by a is 2c. Like that. Equals to, then now the y side, y minus c over b, which is negative c squared plus 1. Like that. And then this equals to the z side, z minus c over then divide by this one right here, negative c squared minus 1. And so we have that, but now calculus book actually gets rid of this. There's too much negatives there, so what it does is well, there's negatives in front, it multiplies everything by -1 and then gets rid of that part right there. So it'll lose multiply by -1, so that just we get equals to x plus 1, just put the -1 at the bottom, -2c, and then equals to y minus c, and then c squared minus 1, and then equals to z minus c, and then c squared plus 1. So there's our symmetric equations of the line. And let's box this in. And now we have to have some disclaimer. So this right here, this works for all values of c except this is where we can't have c is equal to 0, otherwise it's going to be divided by, we're going to go approach infinity, so you can't divide by 0. So c is not equal to 0 for this, you can't use this equation. Not equal to 0, or, in this case here, if we have plus or minus 1, we're going to get a c, we're going to get a 1 minus 1. So -1 squared is 1, minus 1 is 0. So we can't have it plus or minus 1 like that. Alright, so since we can't use c equals 0, so this is symmetric equations for when c is not equal to 0 or plus or minus 1. But for those cases, we could solve those into each manually or individually. So if c equals to 0, then the two planes are given by the equation. So let's write down our first equation, cx plus y plus z equals to c. And then the next one was x minus cy plus cz equals to -1. This is the equations of the plane we were given, or of the two planes. So we have those. And now, if we have c equals to 0, we're going to get a 0. It's going to vanish like that. C times x is 0, plus y plus z equals to 0. And then at the bottom right here, we get, right here, we're going to get a, we're going to get a x plus 0 equals -1. Like that. Yeah, so then this right here, we're going to get an equation y equals, move this z out to the other side, y equals -z. So y equals -z. And what I'm also going to do is, this right here is going to equal to x equals to -1. So our symmetric equations, so instead of the parameter looking like this, we could just, looks like this now. For this one here, we'll have x equals -1 and y equals z. So that's the symmetric equations for that. And now the next one is, alright, yeah, so the next case is if c equals to -1, so let's use that, just plug that c inside there, then the two planes are given by the equations, we're going to get a -1, x, so put the c right here, -1, we're just going to get -x plus y plus z equals to -1, like that. The next one at the bottom is going to be a x minus y, and then minus y, and then plus, or it's going to be -1, so minus, oh yeah, this is going to be c, this is going to be plus like that. So plus y is a negative c, and yeah, -1 times negative there. The next one's going to be minus 1 times z, like that, equals -z, minus 1, like that. Yeah, so we have that. Now what we could do is we could just subtract these. Well, actually, instead of subtracting, we could just add them. We could just add this this entire equation because we have a negative x and x right there. So we could add them up. This cancels out to 0, and we're going to get a plus y is going to be plus 2y. This right here is going to be, this vanishes. The z's vanish. We're going to get plus 0. And this right here adds up, equals to -2. So -1 plus -1 is equals to -2. So in other words, y is going to equal to -1. So this 2 and 2 divided by 2. So y equals -1. Well, instead of circling this, so y equals -1. And what we could do is now if we use this first equation right here and put that down right here and then plug in y equals 1 inside, so we get a like this. Put it like this. We're going to get negative x minus 1, for that's our y, and then plus z equals -1. Yeah, so what happens is -1 and -1 cancels, and move this over to the other side. We just get a simple z equals to x. Yeah, z equals x. So our symmetric equations now for this this case is just y equals -1 and z equals to x. Yeah, so that is that. Let's move this up like that. So there's that. And I just want to make a note right here. So note that the solution manual that I used from the calculus book made a typo in this part and is wrong. And you can I also double checked using GeoGebra graphing calculator. So anyways, so this is right. Whatever if you manage to get the solutions manual, that's wrong. And anyways, I'll just leave it at that. So because they made a typo, they put a negative somewhere where it shouldn't have been, or positive. I forgot what it was. But anyways, now the next one, the last one is if C is equal to 1. Because remember, this fits everything except these 3 cases. So if C equals 1, then the 2 planes are given by the equations. Yeah. So let's write this down. So if C equals to 1, so we're going to have 1 x plus y plus z equals 1. So that's the first equation, x plus y plus z equals to 1. The next one is going to be x minus c plus c z equals negative 1. So x minus y plus z. The c is equals to 1, just goes away. Plus z equals to negative 1, like that. And again, we want to subtract everything, so we get rid of the x right there, because it's they're both the same. So x and x, get rid of those, so we'll get a 0. This y minus negative y is going to be plus y, so we're going to get 2y like that. So plus 2y. Now the z's vanish. The z minus z is just vanished. Now 1 minus negative 1 becomes positive 2. So yeah, we're going to add, so negative is positive, so add 2. So in this case, we're going to get a y equals 2. Y equals 2, well, it cancels out, the 2's cancel, just equals to 1. Yeah, it's divided out and cancels it. So y equals to 1. And then lastly, so this equation 1, put equation 1 right here. Let's plug in y equals 1. So x plus 1 plus z equals to 1. So the 1's cancel. And we're going to get x and move it over to the other side. So we're going to get a z equals to negative x. So there's our symmetric equations for this scenario. So y equals 1 and z equals to x. Like that. Alright, and yeah, that's what we have. And note that the solution manual made a typo in this part as well, and then got the answer wrong. So this is right. Whatever solution manual got it was wrong. And again, we can double check all of our work using we can double check all of our work using the amazing GeoGebra graphing, a 3D graphing calculator. So yeah, we can double check it by graphing in that. The calculator, and here is the screenshots that I use. So here's c equals to 1, plane 1, there's the equation cx plus y plus z equals c, and then plane 2 is x minus y plus c z equals negative 1. And there is our line right here. You could just put in a line point right here, and then we'll have the that normal vector, or in this case going to be the parallel vector to the line, or the direction vector. And then it obtains our line like here, and so on. There's the line right here for the specific case of when c equals to 0, c equals negative 1, and c equals to 1. What I did was I just put points on it, and it formed the line on its own. So you could put negative 1, 0, 0, negative 1, 1, and negative 1. And then to do that, just to illustrate what I meant by that, is if you take this part right here for c equals 0. We end up having this right here. So x is negative 1. So x is negative 1. And then we're going to have, so x is negative 1 point right here. And then the next one is y, 0, 0. So if it's negative 1, and I just put another point. So if it's negative 1, I just put 0 and 0. So if y is 0, z is equal to 0. So I just picked the point on there. And then I picked another point, negative 1, and I put 1 and negative 1. So I put 1 as y, negative 1 there. And it automatically calculates the vector equation of a line. And I did the same thing for this one and this one right here. Just put points in it, it automatically solves it. And then we can graph it out. So here is the line like this. And there's the plane in blue and red. And I'll play around with it soon in the actual website. And also here's the line L. It actually lines up with the equation, the symmetric equation that it was solving, and that lines up when you put c equals to 1 there. So let's go over to here. So here is what I've made, and the other part of the equations are for the rest of this question. So there's the 2 planes. There's plane 1 in red. So what I'll do is some very interesting stuff. So here is initially there's nothing being plotted, or it's just c is being plotted. It's not really. Anyways, so that is the red is this plane, the first one, plane 1. Plane 2 is blue, and you can see is where it's intersecting like that. So it's intersecting right along that right there. And now if I could plug in the line, so there's a line from our point at -1 CC, CC, and there's a vector we put in there, the parallel vector or the normal to the normal vectors. So then put it in, and it exactly fits there. So again, this is how you double check your work. You just graph it as the third party graphing calculator, like this amazing GeoGebra, and it automatically solves that. I think that's how do I shift this over. Okay, shift it over here like this. Yeah, so that is that. And now what I'll do is so this is just general one, but now if the line is L, I mean if C is equal to 0, we have to use a different equation instead of the symmetrical ones, but this one has a vector equation for this automatically calculated vector one. But here's an arc. So if I put this right here, it doesn't line up there. But if I change this if I move this around until it lines up, so I have to go all the way to 1. So there, notice how it's shifting around, it's curving. We go to 0. Yeah, 0. So this is for 0. There's our equation. I just put the 2 points from it and go to 0. There's 0, and it lines up perfectly on it. If I put the line, it exactly lines up with the line. So absolutely amazing. Now if I go to the -1, is down there. So I'll get rid of this. Get rid of this. Or actually keep it like, actually, yeah, I'll just get rid of that. Actually, I'll keep it there. So -1, you go backwards, and then notice it's curving around, and lines up absolutely perfectly on it. It's absolutely amazing. So there's that. Alright, then that last one is 1. And I'll hide that. So notice how far away it is from the lines, and I'll just hide this line as well. Yeah, so it's far away from that, so you got to shift this over to 1. And so, look, it's moving around. The planes are moving based on the value of C. There's a 0. And line exactly in line with that. So anyway, so the answers I gave are the correct ones. Those many had different ones, and those would not line up because they're different. And I already double checked, and there's a line like that. It's absolutely amazing stuff. And again, to reiterate, these lines right here, for example, at L equals 1, I put 0, 1, 0. Well, I just put these two lines and automatically solves for it. All you do is put the points right here, 0, 1, 0, and 1, 1, -1. And to do that, so initially, if I go back to this one right here, so y equals 1, so y is always 1. Then I just put, let's say, 0 right here. It becomes 0. So we have 0, 1, 0. 0, 1, 0, and then another line I put was, this is going to be, let's put 1. So 1 is x, so z is -1. So we'll have 1, 1, -1. So yes, epic stuff. Alright, now let's take a look at the solution to part B. So let's go and read over that question again. Yeah, so part B states, as the number C varies, the line L sweeps out a surface S. And then we're asked, find an equation for the curve of the intersection of S with the horizontal plane Z equals to T. In other words, the trace of S in the plane Z equals to T. So I'll draw out what this actually is asking us to do. It's a bit out there. So let's first visualize the question. So we have the line L. So let's first graph a plane. I'll graph a plane like this. And we'll call this plane right here Z equals to T. So it's a horizontal one. Z equals to T, and let's say we had our line like this. So there's our line L. So we're asked, and then as you vary C, the L is going to move around, and it's going to form some sort of shape. So I'm going to draw this like this. It's going to form a surface around here, and so on. And I'm going to go put a line like this. This is, and then let's just move it around like this. I'll just move it all over, and this is at this point right here. So this is L I'll call LC2, this is LC1, etc. And basically it's going to trace out a shape as you vary the C value. It's going to trace out a shape. That's what we're, and it's going to be trace out a shape on this plane Z equals to T. And we can see this if we graph it out, actually. So here, this is the same link in before. I'll add the link as when we do the double check our work at the end of the question. So if we have this plane Z equals to T, and initially Z is 0.53, so there's the blue line, or the blue plane like that. And there's our equation L from the previous question, part A. So there's our equation for the line L goes through the plane. Now what we'll do is, if we just modify C, we can just press the play button here, and now it's going to trace out a shape there. So we got to find out what the shape is. So it goes all the way here, it's 0.5, and it's going. I have it going backwards. It's moving around like that. At some C values, it moves faster, and it goes like that. around there. So it looks kind of like a circle. So that's pretty cool shape there. So anyways, first thing we got to do is, well, let's and find the basically let's plug in. So if we set z equals to t in the symmetric equations and solve for x and y separately, we get, so basically we're going to plug in z equals to t inside this L and then find out what the x and y are, such that where z is going to be on this plane. Yeah, so first let's take a look at the part A, the solution, where we had the symmetric equations. Yeah, so here's the symmetric equations, and what I'll do is I'll copy and paste these. Oops, like this. I'll copy and paste, and then we're going to plug in z equals to t. So move it down there, and paste it here. Alright, so what we'll do is solve for x and y separately in terms of t. So we'll equate this and this, and afterwards we'll equate the middle one with the z. So we're going to have right here x plus 1 over negative 2c. This equals to, well, z plugged in t there equals to t minus c over c squared plus 1. And now solve for x. Alright, so the next thing to do is multiply this out of there. So negative 2c, move it over to the other side. So this is going to be, we're going to get a x, and also move the negative 1 as well. Move the 1 over to the other side as well. So we're going to get an x equals to, this is going to be a negative 2c times by t minus c, and then this is all divided by c plus 1, and then minus, this is going to be a minus 1. Minus 1 like this. I'll put a 1 like that, yeah, minus 1 like that. And also, yeah, forgot to put a 1 there. So now we gotta just multiply this inside, and also what we'll do is get rid of the, we'll put them all under the same denominator. So multiply the top and bottom by c squared plus 1 over c squared plus 1. So that we'll have this inside. So this is gonna become x is equal to negative 2c times t. Yeah, this is gonna be negative, 2ct, and then move that in, it's gonna be plus 2c squared, and now we have this right here is going to be subtracted by c squared, subtracted by 1, like that, multiply negative 1 inside, and then all divided by c squared plus 1. This equals 2, and this becomes, this is going to be negative 2c t, and then what I'm going to do is I'm going to write plus right here. This is going to be just c squared minus 1, and the solutions might just put this as a bracket there just because we're going to need this later. C squared minus 1 like that. And then c squared plus 1. Yeah, and this c squared is just because 2c squared minus c squared is just c squared, and then minus 1. So we have it like that. Let's put a bracket there just to group these together, because it's going to be some next level stuff soon. Alright, so this is our x value, like that. Alright, now we'll do the same thing for the y. So we'll equate this and put plug in z equals to t there. Alright, so what we're going to get is, so y minus c, so put this like this, y minus c over c squared minus 1 equals 2, and then t minus c over c squared plus 1, like that. And then move this over to this side and move this over to the other side. This equals 2, we're going to get a y equals to t minus c, or c squared, like this. We're going to get I'll put a t minus c, c squared minus 1, and then minus c at the end there, c squared, plus 1, and then minus, this right here is going to be c. So minus c, and then we'll do the same thing, multiply top and bottom by c squared plus 1 over c squared plus 1, and so on. Alright, so then what we're going to get is y equals 2, and we're going to FOIL this out. So this times this is going to be tc squared, and then that times it by negative 1, negative t. Same thing now from the inside. Now we're going to go this times this, and then that times that. We're going to get a negative c cubed, and then negative c times negative 1 plus c, like this. And then move these inside. We're going to have this one here is actually, we made a mistake here, because this was negative c, we moved it over as a plus c. So yes, that's a plus. Yeah, so that's a plus, and then what we'll do is, right here, yeah, so we're going to have to subtract, or just plus this one, plus c cubed, and then plus c, like that. all over c squared plus 1, like this. Alright, just move it over like that. So now we're going to cancel some stuff out. So this cancels with this. And yeah, that's all we're left with. Now we have a negative t, and then this is a 2c there. But what I'll do is I'll factor out the t right here. So this is going to be equals to factor out t. So we're going to get a c squared minus 1. And then t. And then the next one is just plus 2c. So this 2c is right there. Plus 2c, all divided by c squared plus 1, like that. So that's why in the first one we had the c squared minus 1. Just put that in a bracket because we have this one here as well. We can do some interesting stuff with it soon. Alright, so going further, so to eliminate c from these equations, we can work with squares, x squared and y squared. Yeah, we'll put the, yeah, we'll work on this instead of just working it regularly. And again, this is a pretty next level a solution that we're going to go over. The solutions manual just gave the answer, didn't actually explain how it got here, so I had to find one online. So basically, what we'll do is if we'll let's write out our x1, x equation right here. So we'll do the first one, x like this equals to negative 2c, just put it all out like that, and then plus c squared minus 1 over c squared plus 1. So first what we'll do is divide this out, just separate the terms. So negative 2c like this over c squared plus 1. And because of the t value there, I'm going to put a t like this, and I'll move it over to the other side. This will make sense as we get through it. And the next one is the c squared minus 1 over c squared plus 1, like that. And this is going to be minus t like that. Alright, so now note what happens here. If we look at these two terms right here, if we square and add them, notice what happens. And note, so if we have c squared minus 1, and you can kind of see the pattern that's going to arise, and then this is c squared plus 1. So if we square this, and then add the other one, 2c like this, c squared plus 1, and then this is all squared up, move that bracket there. C squared plus 1 all squared. Yeah, so what we end up having is, so if we multiply this top part here, c squared minus 1 squared, so that's going to be c squared times c squared, c4, and then c squared times negative 1, that's going to be negative c2, and then negative 1 times c squared, again put at negative 2 there as well. And then the next one is, this is going to be negative 1 times negative 1 is going to be plus 1. And then that's the top. And then this next one here is going to be plus, put the all in the same common denominator. Right here, 2c squared is going to be 4c squared. And now the bottom here, we're going to have c4, c squared times c squared. Yes, when you square c squared squared, c squared plus 1 squared. C squared times c squared is c4, c to the power 4. And then this one, c squared times 1. That's going to be c squared, and then 1 times c squared, another 2. So notice the similarities right here. And then this is going to be plus, and then this is going to be, yeah, the last one is just 1 times 1. Is 1. Alright, and now, see, notice what happens here. We have c4. Yes, we have c4 plus 1, so this matches up with this at the bottom. And this one right here, this cancels. We're going to get left with a 2, so 2c squared. So in other words, this entire thing equals to 1. So this all equals to 1. So that's that. Alright, so what we have now is basically a trigonomic identity. Well, we could write it as that. So what I'll do is I'm going to let this middle one right here, let this equal to cosine theta, and this inside as sine theta. So in other words, we're going to let c squared minus 1 over c squared plus 1 equals to cosine theta, or cosine theta, and the next one is 2c over c squared plus 1 equals to sine theta. So if we let that equal to it, and then we just get the identity, we just get the identity right here. We're going to get cosine squared theta plus sine. So when we square this equals to 1, and then again, we already know this identity. This is already a trigonomic identity, so this is true as well. So we have that. Yeah, so that's what we have is, so we have that now. So I'll write thus, thus x. Now we just replace those inside. So this is our x value right here. So negative, this is c squared minus 1 plus c squared plus 1. So that's going to be cosine, and this is going to be minus sine, and there's a t. So this is going to equal to, yeah, it's going to equal to cosine theta, and then minus sine theta t. And likewise for y, because y has the same components, but just different order and so on. So if we go to the y is right here. So c squared, so this one here divided out. So c squared minus 1 divided by c squared plus 1. So that's just cosine. And then we have a plus now. So it's a plus like that. Yeah, except there's a t there. There's a t there. And then there's a 2c over there. So we'll move it around to the other side. This is going to be actually the other way around. This is going to be cosine t. And this is going to be sine theta. Move the sign in front. So there's the 2c over c squared plus 1. And yeah, that's our 2c over c squared plus 1 is sine. Move that over to the front so we have t on the other side. So there is our equations like this. Yeah, so we have these in this format. But what we could do is we could square them. So thus, or double thus. So if we square them, so we could apply this trigonometric identity to help out cancel stuff as we'll go through it. So if we do x squared plus y squared and see what happens. So we're going to get a, because again, we've got rid of c. There's no c in this. There's a theta instead of c. So cosine theta is equal to these, and sine theta is equal to that. So we got rid of the c. And now we just got to simplify this further. So this is going to be a segment here. So cosine theta minus sine theta t. So square all that. This is going to be cosine times itself, like that. The cosine theta squared, and then cosine theta times this one. We're going to get a sine theta cosine theta t, and then do the same thing. Negative over here times it by cosine. So we'll have a 2 there. And then this times it by itself. So negative, so basically, again, we're just foiling out, just doing it in our head. So negative sine theta times negative sine theta t. So we're going to get a plus sine squared theta t. Like that. And now do the same thing for the bottom right here. So sine theta plus cosine theta t all squared. So sine theta times sine theta is equal to, this is going to be a sine squared theta. The next one right here, this is going to be sine theta times cosine theta t. That's going to be, well, it's going to be a plus sine theta cosine theta t. And then likewise, what we'll do is multiply this out as well. So then now going over this side, cosine theta t times sine theta, add another 2. And then multiply this by itself, plus cosine squared theta t. Alright, so what we end up having is, well, this equals to 1. This part right here equals to 1. This is just 1. Yeah, so put all of this equals to 1. Now this right here cancels. So we have, there, which is cancelled. It's going to be equal to 0. And then plus, right here now we have the sine squared theta plus 1 here. We can factor out the t. So what we'll get is a sine squared theta plus cosine squared theta t. So in other words, this equals to 1. So that's this equals to 1. So what we end up having is 1 plus t squared. That's all that algebra, and put this down here. So we got some epic stuff here. We get x squared plus y squared equals 1 plus t squared. And this is just a circle. This is circle. Circle of r. So r is going to equal to, well, the square root of this 1 plus t squared. And that's because when you have the x squared plus y squared, the right side is just going to be the radius squared. So it's going to be r is equal to 1 plus t squared. And it also has origin. And I'll write and origin. The origin is going to be at, well, in front of this one. Well, there is no x minus anything. So there's no x minus a or y minus b. So in other words, the origin is at the center. So origin is going to be at x equals 0, y equals 0. And it's all on the t plane because we're in 3D, so we'll just put a t, like that, z equals to t plane. Yeah. Alright, then now we can graph this all out and as a way to double check all of our work using the GeoGebra 3D graphing calculator. So here is the C value where we can modify it. Here's the line, and basically here is the T value. So we have T, you can modify it, and so on. And also here's the surface S. When you plug it in, if you plug in Z equals to T here, it just becomes a cylinder, a circular cylinder. And if you just put it as Z as just a regular, just a variable, this ends up becoming a hyperboloid of one sheet. So notice, this is it becomes literally a hyperboloid. There's the shape right there formed by this line L. It's perfectly on it the whole way, and then as it rotates, it forms a circle. So it forms a circle like that. Yeah, so it's a circle there. If you put T as Z equals to T, it becomes a circular cylinder, and I'll show that soon. Like that. Yes, that's what we have. And then also note here, note that the surface S, or which is just x squared plus y squared minus z squared equals to 1. Just move this over to the other side. Is a hyperboloid of one sheet. So it looks like this. So hyperboloid, basically a hyperbola on the top, like that, cross sections. And it's on every intersection, even if you cut it along this this plane, like here on the y plane, you're going to get another hyperboloid like that as well. And horizontal traces, though, are ellipses. So yeah, so if you cut it like this, you're going to get an ellipse, but it circles, again, the type of ellipse, a symmetric ellipse. You're going to get it shaped like that, and so on. So ellipse or circle, depending on the type. And vertical traces are hyperbolas, and the axis of symmetry corresponds to the variable whose coefficient is negative. In this case, we have negative z, so negative z, so the axis is going to be the axis of symmetry there. So let's go and look at our graph right here. So this is right here is our graph. Yeah, so here's what we have. So first thing we can do is, if you have the C value, if you modify C, notice that it moves around around in a circle there, but in a hyperbolic or hyperboloid of one sheet. It's always around there. Notice forming a perfect circle around this plane like that. Yeah, so that is our circular there. And going further, so this is a hyperboloid, and there's the horizontal plane z equals to t is in blue, so you can modify this, and you'll see it goes up and down. So modify, this is a value I don't need. Delete this one. This is the value I need. Okay, so there it is. If you move it up and down, just a circle part in there gets modified. Like that. And also what we could do is, if we change this into a T, or I'll copy and paste this, so I'll put a T there. If you put a T, it just becomes a cylinder like that. Yeah, cylinder. So I'll change this back into Z. I'll pause this and go to, this is going to be Z. And yeah, so that's going to be our Z. So that's a hyperboloid shape like that. So that's epic stuff there. And so I'll just copy and I'll duplicate this right here. Duplicate input T like here. And just stop here. And then T like that. So there's our shape there. And this goes directly inside that circle there. And yeah, that cylinder, it strikes right at wherever the plane is. So if we go change the plane. Yeah, so it's a very advanced. Yeah, so you can see the plane going, changing the size of that cylinder, but always in line with this hyperboloid of one sheet. So it's epic stuff there. So I'll just hide that. So yes, amazing stuff. So we play around with that, and I will just save this. All right, so yes, that's pretty epic stuff there. Alright, so now let's take a look at the solution to part C, and if we scroll back all the way up to part C, yeah, and so read that out. So part C, we're asked, find the volume of the solid bounded by S and the planes Z equals 0 and Z equals to 1. Alright, so let's take a look at the solution here. So since we know the cross-section of the hyperboloid of one sheet, surface S, so again, the surface S is a hyperboloid of one sheet, and we know that the cross section is a circle, and we know its radius. We can determine the volume, volume of S between the planes Z equals 0 and Z equals to 1. So in other words, we just have two planes, and then basically set up an integral. So if we have our let's say our hyperboloid of one sheet like this. So it looks like I'll do a cross section right here. So let's say we had I'll just do the full thing like that. That's the full thing. So we're gonna do 2 planes like this, and cut one of them there, and then one is slightly higher like this to cut them over there, and then let's move it down here. So we have the shape like this. It looks a bit whack. This is z equals to 0, and this is, let's say z equals to 1, and we know the shape here is a circle. So we know this right here, and we know the area. That's just area is pi r squared, and then we just take a infinitely small thickness. We'll call that d. We don't even need to draw it. I'll just write this here as, we know this area. A at z is equal to pi r squared, and we know r is equal to, or we know r squared. R squared is just equal to, if you scroll all the way back here, right here. So r squared is just equal to 1 plus t squared. But that's at z equals to t. But so in general, it's just going to be 1 plus z squared. Yeah, so it's going to be 1 plus z squared. So this is going to be pi 1 plus z squared. And yeah, for completeness, I'll just take an infinitely small thickness right here. So we take a slice like this. And all right, so there's a slice. I just drew it all over there, and this is going to be our dz. So basically, infinitely small thickness. So then that means we could just take our integral. Yeah, so this means that v is equal to the integral from 0 to 1, the planes, and then az dz, like that. And again, that's the infinitely small thickness right there, dz, multiplied by az, so you get that infinitely small volume there, and we just integrate it over the entire length there, or entire thickness from z equals 0 to 1. So in other words, let's put the v here now. This equals 0 to 1, plug in our a and z, a of z, the area. It's equal to pi 1 plus z squared, 1 plus z squared inside dz. This equals to, take integral, put the pi out of there. This equals integral from of 1 is just be z. And then integral of z squared is equal to z cubed over 3. And then this equals 2, well, and this is going to be from 0 to 1. The range 0 to 1, this equals to pi times it by, put the 1 there, 1, plus 1 cubed, and also multiply top and bottom 3 by 3, plus 1 over 3. And then minus, this all just vanishes 0, just like that. So then this ends up equaling, right here, v is equal to, so 3 over 3, just plus 1 over 3, that's just going to be 4 over 3. This equals to 4 over 3 pi. So there's our volume. Yeah, pi like that. Put this a bit neater. So pi. So there's our volume of the solid there. Alright, so yes, amazing stuff there. Alright, so now let's take a look at problem 4, and this one is about a plane flying in wind. So a plane is capable of flying at a speed of 180 kilometers per hour in still air. The pilot takes off from an airfield and heads due north, so he's going pretty much, yeah, just straight like that, straight up north, according to the plane's compass. After 30 minutes of flight time, yeah, the pilot notices that due to the wind, the plane has actually traveled 80 kilometers at an angle 5 degrees east of north. So it actually flies over here, kilometers. So 5 degrees from that over there. So we're asked a two-part question. So part A, what is the wind velocity? And B, in what direction should the pilot have headed to reach the intended destination? Alright, so let's take a look at the first part. So solution to A, so we consider velocity vectors for the plane and the wind. So we want to find out what the wind velocity is. So let's write these in vectors, and let VI vector be the initial or intended velocity for the plane, and let VG or subscript G vector be the actual velocity relative to the ground. Because again, you have the plane like this, and it's flying, and so you're flying straight. But then even if you're pointing north there, you could be being pushed across by the wind. So you could be over here, a really bad plane. like that. So anyways, you could be drifting across, but even though you're still pointing the nose forward. And also, if W is the velocity of the wind, Vg is the resultant. Vg is the resultant. That's actually the actual velocity. That is the vector sum Vi plus W as shown in the figure. So let's say you're flying across here. So put a dashed line like this. I'll just put a flat line so we get the angles. So it's flying straight due north. This is the intended Vi. So we want to go Vi here. But what we end up actually flying towards is we fly 5 degrees. We'll put a 5 degrees like this. And yeah, we end up flying over here at an actual ground velocity, or the resultant here. And we're going to have a wind direction. I'm going to put a W like this. So that this is a vector sum there. So we have Vg like this is equal to just basic vectors, Vi vector plus W vector. And also, if this is 5 degrees and you're going due north initially, the intended scenario, so then this angle is going to be 90 minus 5. So this is a right angle like that. This is going to be 85 degrees. All right, so continuing further, so we know that Vi, we know that this vector, this is the intended velocity, and that's just going to be 180j, and this is due north again in our ijk components. Like that. That's basically going in the y direction, or the north direction there. So again, it was 180 kilometers per hour is the intended velocity we were going at. Yeah, so that is there, and then let's write this out. And since the plane flew 80 kilometers in a half hour, the absolute value of this ground velocity is going to be equal to 160 kilometers per hour. Because again, that's 80 in half hour, so times it by 2, 160. So it actually got slowed down, so some of the wind is hitting it directly at its face, so it's actually going down as well. So then you can see that here, I have 30 minutes of flight time. The pilot notices plane has traveled 80 kilometers at an angle 5 degrees east of north. Yeah, so thus we have, and what I'm going to also do here is, first of all, we're going to determine this Vg as a vector. So to do that, well, we could notice this part right here. So we could take that, so it's going like this. This is Vg. This is Vg like that, and yeah, I'll just put a Vg like that. And we also know that this right here is 85 degrees. And again, using basic trigonometry. And then this height right here, so I'll erase this, goes like this. Yeah, this right here I'm just going to put like that. And using trigonometry, this right here is the tangent, the sine of this one. I've included this one here. So this is going to be the absolute value of Vg like this, with this is the full distance right here. Absolute value of Vg like that. And that's going to be, this is going to be sine theta. As again, remember, sine theta is equal to opposite over opposite over hypotenuse. And then so the bottom right here is going to be Vg, the absolute value, sine times by cosine. So the adjacent over hypotenuse. And then just move over the hypotenuse to get the adjacent. Yeah, so basically writing these in components. So this Vg, so Vg as a vector is going to be, well, the Vg velocity, ground velocity or resultant, etc., is going to equal to, we just add the component. So the horizontal component in the I direction is going to be Vg cosine theta I plus, and then the vertical or the north direction is going to be, this is going to be an absolute value sign right here. So the absolute value sign, again, velocity has direction, magnitude doesn't, right there. The speed doesn't. Like this. This is going to be sine theta j. And we know the absolute value of the ground velocity, that's just going to be, the speed, so 160 kilometers. So 80 times 2. Yeah, so this is going to be, the I components will be 160 cosine, theta is 85, and then this is going to be our I, plus 160, like that, and then sine 85 degrees, and this is our J component. And now plug this into the calculator, we're going to get roughly equals to 13.9 I, and plus 159.4 J. And yeah, we can just box this whole thing in. Alright, so that's what we have there. Now we can do a quick calculation check. So my OneNote has a built-in calculator. So you can just go erase this, just put cosine, yeah, so 160 times cosine 85, and it's automatically in degrees, and it goes 13.94549, etc. And then similarly for this one, 160 times sine 85 degrees, 159.39, rounded up 159.4. So now we could solve for the wind velocity because we have both we know VG and we know VI, so we should solve for W. So basically, we'll have VG is equal to VI plus W, like that. Plus W like this. Yeah, so in other words, we're going to have W, let's put an arrow here, plus W is equal to, this is going to move this over to the other side, so we're going to get a VG minus VI. So we have to subtract vectors, and we can do this, yeah, but let's just write the components out. We could write them in IJ or just write them as a vector bracket form. Well, I'll write this one right here. So VG is equal to 13.9 and 159.4. 13.9 and 159.4, and then subtract this by VI. And VI we know is just going due north, so the horizontal component is 0, and then the other one's 180, is the vertical. Alright, so if we subtract these, what we end up having is 13.9 minus 0 is just 13.9. So this is going to be 13.9. And then likewise here, 159.4 minus 180. Yeah, so here we need to do some subtraction since this 159.4 is on the other side is minusing. This one is bigger. What we could do is do it manually. You put 180 on top and then subtract this by and put a negative all over the whole thing. So put a negative like this, like that. So we're just going to do this all by hand manually just for fun sake. 180 minus this 159, so the difference, 0.4, 0.0. But then we're going to get a positive number, so we need to add a negative to it. Like this. So we're going to get a positive. So I will bracket this and put a negative. Alright, here, just fix that up, and now we'll just solve it. So this one here, this is 0, minus 4, we need to basically add a 1 here. So we need to subtract one of these, but because there's already a 0, this is going to be a 9, and this crosses out to a 7, so we take 1 away. This becomes a 10 right here. So this is going to become a 10, like that. So we have 10 minus 4 is 6, and then 9 minus 9 is 0, and then 7 minus 5 is 2, and this goes 1 minus 1 is 0. So we have 20.6, and we have to put a negative because we flipped over the bigger number on the top. So this is going to be equal to negative 13.9 and negative 20.6, or you could write this in IJK format. This equals to 13. Yeah, let's put this again. Yeah, so 13.9I minus 20.6J. And this is the wind velocity. And likewise, the absolute value of it, or the wind speed, is going to equal to, this is again relative to the ground, just whatever it is. Yeah, so the actual speed of it. This is just the velocity includes direction. So we just take the, basically, take the square root of it. I mean, we just use the basic magnitude formula, and that's just the Pythagorean theorem, basically. We just sum these up and square them. So square and sum it up. So we're going to get 13.9 squared plus 20.6 squared, like that. And plug this into the calculator, we get roughly, this will equal to 24.9 kilometers per hour. And that is our wind speed. Alright, so continuing further, I'll just do a quick calculation check right here. So square root 13.9 squared plus, and then negative 20.6 squared. And yeah, this is a negative. It doesn't change anything. There's a negative like that. It's still going to be, squared there. It's still going to be positive. So we put that in like here. This equals to 24.85, and then round it up to 9 there. And also here, just to double check my manual subtraction there, You just put this here, 159.4 minus 180. This equals to 20.6. Alright, yeah, so now we have it all correct. So now we can move on to the solution to part B. So let's go and read that again. So part B says, in what direction should the pilot have headed to reach the intended destination? Alright, so let's draw this out. So basically we have to fly to the west, and then it will hopefully go to the north. So let V be the velocity the pilot should have taken, and the pilot would need to head a little west of north to compensate for the wind. So let theta be the angle V makes with the north direction. Alright, so let's graph this out. So let's say we have our ground speed, it ends up going over here, VG. I'll write this as VG like this, and this is our due north is where we want to go. So then this is going to be right angle like this, and now we're going to fly a bit to the west. So this is our V, like that. So that's our V, and this is at an angle theta west of north to compensate. And now we have our wind. It's going to be pushing this way, the same direction, W, like that. So wind is always the same as the previous one. And now what we're going to have is, we'll have another right angle right here. And so I will extend this out. Yeah, I'll extend this out further. So what we end up having is a right angle like this. And this one is going to be this angle right here. Well, instead of looking at that, we could just use the full 90, just the full thing right here. So 90 degrees plus theta, and then and I'll show you why it's the same thing. And what we end up having is this side length right here is going to be this is going to be the magnitude of the velocity we want to go, so the speed times by sine theta, similar, just using basic trigonometry. This is sine theta plus 90. Yeah, and let's put this is actually 90 plus 90 degrees plus theta. And yeah, so we have this right here, but notice we could also use you could also use cosine here. Cosine instead of we can use the cosine of the theta angle and use it over on this height. But the thing is, with this case, we have to always keep in mind where is negative and where is positive. I'm just going to keep it like this because the solutions manual has it like that. Because if you go on the left side right here, this one will be sine. We're going to be positive number, but it's going to the west. And then in this coordinate system, we have west is a negative. Because we have this angle going from this side here, where 0 is on the positive axis, on the positive x-axis there. So anyways, the next part here is this is the absolute value of the speed, and then cosine 0 plus 90 degrees, like that. That's the cosine of it. And again, just a note, this right here would be, this is going from backwards over there. This is the same as writing 90 minus theta. Or we could use it over there. Again, depends how you want to look at it. But if you just recall the trigonomic, for example, cosine, and same thing for sine. So I'll just put cosine right here. Cosine theta. So cosine theta looks like this and goes up like that. This is at pi or 90 degrees. That's at 90, and this is at 180 or 270. And 180 is right here. So so basically, if we have, and it's symmetric. So let's say we had an angle across here. This is between here and here is theta. So if we go 90 minus it, we're going to have a positive number, but we want an actual negative there, so we'll have to put a negative if we use this one here. And then, but then if we go across to the other side, so right here, this is, I'll put it like this. This right here, theta. So basically, basically 90 plus theta will have a negative number, which is what we want. So it's exactly the same thing. This is going to be plus. This is going to be negative, and exactly the same thing. It's just symmetric. But all right. So now that we just established that, I just wanted to do a quick sidetrack on trigonometry to understand. You could just use the full angle wherever the line is. If you go all the way around, you can just add. Just ignore how the triangle looks like. It's going to end up being the same thing, but the signs always are kept under track. So basically, continue further. So with effect of the wind, the actual velocity with respect to the ground will be v plus vw. So Vg is there. which we want to be due north. So what we'll do is VG is equal to, and again add the vectors, V plus W is equals to V plus W. This equals 2, and let's just all write it out in component format like this, or vector bracket format. So V here is going to be, this is going to be the absolute value of V. This is 180. I'll just write it all down quickly. So 180, and then sine like this, and we need to find out that angle. So it's going to be sine theta plus 90 degrees, and then the next one is going to be, actually no, this is the other way around. This is a cosine. This is the horizontal one. This is the I component, and then the next one is the 180, like this. 180, and then this is sine theta plus 90, like that, and then we have to add the wind, plus the wind is going to be, and we already know the wind is this here, 13.9 and negative 20.6, but instead let's just use the full values, and the full values here, this was the VG, and we just subtracted by 180 on this other side there. So instead of actually solving it all out, I'll just use the exact numbers. So this would be 80 cosine 85. So this is yeah. So this one, the first part right here, this is 13.9. Is this the is 160 cosine 85. So I'll just go plus 160 cosine 85 degrees. And again, just because the solutions manual did that, it's easier to work with. I guess it's just more accurate instead of having to always use the approximation format. Then the next one is going to be 160, and then this is going to be 160 sine, so 159.4, and then subtracted by 180. So sine, so 160 sine 85 degrees minus 180. So just put it all together like that. All right, and now we want this to be 0. So the horizontal component, we want it to be 0. So we want it to equal to 0. And then on the other part, we just add those up. So we'll just have 180 sine. Yeah, because that's the thing. We want it to be due north. So now we just have to find what angle it is to make it 0 there. And this can be sine theta plus 90, like this. And then this is going to be, now we just add this part here, plus 160 sine 85 degrees minus 180. So that is our velocity. And so we want this part right here 0. So to do that, we need to equate, or just sum those all up to 0. So in other words, we want, so 180 cosine theta plus 90 degrees plus 160 cosine 85. When you add the horizontal components, we want it to equal to 0. So we want that, so now we just got to solve it. And to do that, let's move things around so that we're going to have a cosine theta plus 90 degrees equals 2. Move this over to the other side. So negative, and also divide this out. So we're going to get a negative 160 divided by 180, and then a cosine 85 degrees. All right, now if you plug this into the calculator, you're going to get, this part's going to be equal to roughly negative 0.0775. And so this means now we got to solve for theta, and we just take the arc cosine of it. So theta is going to be roughly equals to, because we're using approximate form right there, 0.007. So it's going to be roughly equal to the inverse of cosine negative 1. We have power negative 1, just the inverse cosine or a cosine or arc cosine. Now it's going to be, this is going to be negative 0.0775, and then minus, move this over to the other side after we get that out, so minus 90. And now this roughly equals 2. Yeah, this is going to equal 2. This is going to be, it's going to be equal to 4.4 degrees, and I'll show you the calculation too. And this is going to be due west. So I'll put this like this, like that. Yeah, so basically, thus the pilot should have headed about 4.4 degrees west of north. And here's a quick calculation check. So negative 160 divided by 180 cosine 85. Plug in the calculator. One note built in. and automatically solves that. So negative 0.00747, rounded up to 5 there. And then also a cosine, you could just solve this for the angle, equals 2. And I put the exact one here. I just put this whole thing inside here instead of using this rounded up one. So negative cosine 60 divided by 160, 180, cosine 85, all that minus 90. You can do that, all that, and it solves it automatically over here. And also, lastly, I added this one right here because we didn't need this part. We weren't asked, but we can use this to solve the ground velocity. And basically, it's heading due north, so all we need is the j component. So 180 sine theta plus 90 plus 160 sine 85 minus 180. So plug that all inside, and I just use this 4.44, just easier. Just round it up. So 180 sine 4.4 plus 90, and then plus 160 times sine 85 minus 180. Plug this into the calculator. We get 158.86. So I round it up. So the final ground speed is about say approximate, not roughly, it's pretty accurate. So it's approximately 158.9 kilometers per hour, which is a bit slower than the previous 160 kilometers per hour. That was the ground speed that we were initially going if we had due north. Because this time we are headed more head on against the wind, because the wind's going this way, and now we're going to be, initially we were going this way, now we're going flying over 4.4 degrees more head on, so we're going to slightly go slower. So the final speed is actually going to be a bit slower. It's going to go down a bit. So it's not the 160 kilometers per hour. Now it's 158.9. So it's a tiny bit slower. Yes, epic stuff. All right, now let's take a look at the next problem, and that's problem 5. And this involves the sum of vector projections. This can be a very interesting problem right here. So suppose V1 and V2 are vectors with the magnitude of V1 is equal to 2, magnitude of V2 is equal to 3, and their dot product V1 dot V2 is equal to 5, and let V3 vector equal to the projection of V2 onto V1, and let V4 equals to the projection of V3 onto V2, and V5 is the projection of V4 onto V3, and so on. And we're asked compute the sum from n equals 1 to infinity of the magnitude of Vn. So just sum up all the magnitudes and then find that infinite sum there. So that's an interesting problem there. So let's take a look at the solution. So first off, let's recall the dot product and vector projections. There's a dot product right here. Recall from earlier videos. There's thumbnails to both of them and links to both. So the dot product, so A dot B is equal to just A1 B1 plus A2 B2 plus A3 B3. So basically you multiply each component, and we multiply the components and add them up. And it's also equal to the magnitude A times magnitude B cosine theta. And so the angle between them is also involved as well. Or that's a geometric interpretation of this dot product. Alright, so that's by definition, that's what it is. And the projection, if we recall, if you have a vector B and you have vector A right here, so then this, if you project this one onto here, you're basically taking, for example, in this case, you're going to take, this is the angle theta, you're taking the cosine on it. So you would write projection of B onto this vector A, like that. So as a vector projection, and if you recall my earlier video, I showed that it's equal to the dot product of the two vectors divided by the magnitude, and then times it by the unit vector of A, which is A over its magnitude, and you end up getting this right here. And then the component is the actual size of this over there. So there's a component of B onto A, and that's just A dot product divided by A. So there's the same thing right here. They take a component, but then you have to multiply by the unit vector to get it into a vector. And unit vector is just going to be a size 1. That's all it is. But it's along that direction of A. But anyways, so that's that. That's a quick recap. So now let's calculate out the projections and try to find a pattern. So let's write down what we have. So we know that this length right here, what we're interested in is just the magnitude is mainly. We're interested in the magnitude, but nonetheless we know the dot product, so we could use those. Alright, so we know that the magnitude of V1 is equal to 2, and so that's 2, so we have that right here, 2, and then magnitude of V2 is equal to 3. And we know V2 is equal to 3. Like this. Basically writing out what we are given. Yeah, so this equals to 3, and then the dot product V1 dot V2 is equal to this will just be equal to, right here, v1 dot v2 is equal to 5. Like that. So now the next setup is, so then the v3, so we have the v3 is a projection like this. This equals to, we're given as a projection of v2 onto v1. And it's always the same pattern. So projection of v2 onto v1. So the later one onto the first one. And then projection, we just use a formula. I'll recall the formula. This is going to be a dot b over a magnitude squared of a times a. So this is going to be a dot b, or in this case, it's going to be v2 v1. So a in this case is we have, this is the a1, this is the b1. So a is over there. So basically, it's going to be v1 dot v2 over v1 magnitude. And yeah, squared right there. So there's a squared there. So yeah, and then multiplied by the v1 vector. Like that. So this equals to v1 dot v2. We know that is dot product is equal to 5. And then divided by magnitude squared of v1. That's going to be 2 squared. And then this one right here is just going to be v1. Like that. So we know this part right there. So that's that vector. Then what we want to know is the magnitude. So and then the magnitude of it. This just means it's just so v3 is vectors the same as v1, but scaled up by 5 over 2 squared. So this means then if we just take the absolute value sign like this is just the magnitude. This equals 2, 5 over 2. So it's the same thing as magnitude of this one, but scaled up. And we know the magnitude of v1 is just, 2. This equals to 2, so basically this is, I'll just put it 2 like that, or I'll just complete it, fill out the full thing. So 2 and 2 squared times 2, and this cancels out. We're going to get left with 5 over 2, so one of the cancels. It's power of 1, this cancels with this. So that's 5 over 2, like that. Alright, so I'm going to box that one in, but I'm going to circle this because we will need this. So the next one is going to be v4. So v4, following the same pattern, is a projection of v3 onto v2, and this equals 2, and this is going to equal to, what's the next one right here? Yeah, this is going to equal to, just apply the same formulas. This is going to be v2 dot v3 dot over, and then v2 magnitude, like this, squared, and then the next one's going to be, well, v2 there. Like that. Alright, so now what we could do is, the next setup is, well, we could plug in our values that we know. So we know v3 is equal to this right here. So we could circle that in here and put that inside. And this one here, v2 is just 3 squared, so we could put that in. This equals to 3 squared. And yeah, the next one is going to be, this is v2. I'll move that in this side right here. v2, and then move in this v3 inside. We'll have a 5 over 2 squared times it by v1. So we have the dot products line up like that. Let's put it like that. And this is going to be, the next one's going to be v2 like that. Alright, so then this dot product is going to equal to, well, that's just 5. So put these all together. This equals to, it's going to be 5, and then there's already a 5 there. So 5 squared, and then this bottom part is going to be 2 squared, 3 squared, and then the next one is this v2. Like that. Yeah, so we just block this out. Again, this is just 5, and then times it by that. 5 over 2. So let's leave it like that. Alright, so that's that. And now the next setup is, well, we have that and then what we're going to get is the v4 vector magnitude of it. This equals 2. Again, it's just a constant multiplied by the vectors, same thing, just scaled up. So it'll be the same thing, like that. Yeah, but then multiply by those constants. And then v squared, v magnitude like that, v2. And v2 is just equal to 3. So then that equals to 3. We'll put another sign right here. This equals to 2, and so on. So this 3, this is going to cancel out. So we're just going to left with 5 squared over 2 to 2 and 3 to the 1. I'll box that 1 in. I'll put the 1 there. So we know the pattern right here. So initially we have 5 over 2, So we have 5 there, yeah, but yeah, we have 5 over 2, 5 over 2 squared, and then there's a 3 to the power of 1. All right, now we have this. Now to do the next one, let's just do one more, then you could see if there's a pattern that arises, and so on. All right, so the next one is going to be the V5. Again, the same exact setup there, projection V4 onto V3. This equals 2, and this is like this. This equals 2. And let's just write this down. This is going to be the V3, because that's our new A, and then V4 is our new B. So dot product with that, and divided by magnitude V3 squared, and then V3 vector. Like that. And then we know what V4 is. V4 is this. So circle this, replace that with it. So what we end up having is this equals 2, and move that in the front. We're going to get I'll put these outside of it, 5 squared over, this is going to be 2 squared, and then V3 squared, so we know V3 is equal to 5 over 2. So that's going to be equal to, we'll do that afterwards, this squared, this is 3 squared, and then we have this 5 over 2 squared. I'll put a 5 over 2 squared. Alright, and then the next one is, we'll put this one in here, this is the V2 now. V2, and then there's the V3 dot, and then we have, V3 like that. So these are dot product in there. Yeah, also, actually, we forgot to do another part here, actually. This is we replaced V2, we forgot to do the V3. So I'll move this over, so replace that as well, and V3 is equal to this one. So again, we have it a bit backwards, but it's close enough. So this is going to be times it by, I'll put this 5 over, let's put this in here, 2, like that, V1 squared, a V1 vector like that, and this is all V3. Like that. So let's see what we end up having. Alright, so we end up having is, well, let's see what ends up happening. So this would cancel with this, this 5 over 2, that's the same thing as writing 5 squared over 2 squared. And then this will cancel as well with this. So what we're left with is, and also there's a V2, I'll put that together actually. This equals 2. I'll put that in front, V1 dot V2, just make it a bit easier to see. And the top is going to be, there's a 5 included. And I'll just move it over. So, this equals 2. And let's erase this all. And then this is going to be 5 times it by, V1 dot V2, move it other side, you could do that. And this is going to be now, this would cancel with this. 2 over 2, 3 over 2, times V3, like that. And, then this one here, V1 dot V2 is just 5. So we're going to have 5, again, this is 5, so 5 squared, like that. 2 over 2, 3 over 2, and then V3 squared, V3 vector. And then this means that, and we'll have V5 vector magnitude is equal to 5 over 2 over 2 over 2, 3 over 2, and then this right here, magnitude of V3. And V3 magnitude is just, we already know that, that's just 5 over 2. So this is going to be, again, 5 over 2. Like that. Like that. And then this is going to be then 5, 3 over 2 to 3, and then 3 to the 2. And we pretty much have a pattern here. So there's this goes 5, 2, 2, 2, and then 3, 1. This 5, 3, 2, 3, 3, 2. So there's 1 power less on the 3. This one right here is 5, right here. Actually, this is right here, 5 and 2. In other words, that's a 5, 1, 1, and 3, 0. Or this equals to 5, 1, 2, 1, and 3, 0. Like that. So then the next one is going to be 5, 2, 2, 2 to the 2, 3 to the 1. Then the next one, 5, 3, 2 to 3, 3 to 2. Yeah, so similarly we get is a V6 is going to equal 2, just increase the powers by 1. 5, 4 over 2 to the 4, and then 3 to the 3. Like that. And V7 vector magnitude is equal to 5 to the 5. Like that, over 2 to the 5, and then 3 to the 4. So just add up 1 each time. So in general, what we'll have is Vn, let's go, V sub n vector magnitude is equal to, this is going to be separated by 2. So if you had a 5, you had a 3, you had a 6, you had a 4. If you had a 5 if you had a 4 right here, you end up getting a 2. So and this one is a 3 there. So you subtract by 2 or 3. So this is going to be equals to 5 n minus 2. And then divided by 2, this one's going to get n minus 2. And then 3 n minus 3. And now what we could do is to get to the same power, because these are n to the negative 2s, and then the negative 2s, and the negative 3. So what we could do is multiply the top and bottom by 3 to the power of 1, so it's 3, like that, so that this can add up to it. So n minus 3 plus 1, so this would equal, these two would equal to 3 n minus 2, like that. And then all we're left with is just an extra 3 on top there. And also this 3 can multiply it inside there. So this equals to 3, and these are all the powers, so we can just take it all out of there. This equals to 5 over 2, and then we could bring that into 2 times 3. So 2 times 3 right here is going to be 6. And this is all to the power of n minus 2, like that. So that is what Vn is. So yes, we just box this in. Yeah. All right, and here I'm going to write this instead. I'll write this in general, because we're going to have another... so in general so now we have another thus. So now thus, let's just calculate the entire, the sum. So we're asked for the full sum right here. So sum of all these from n equals 1 to infinity. So, see how this was written? Yeah, it's fine. So we'll write is, so thus we have the summation from n equals to 0 up to infinity of Vn, put it, the magnitude Vn is equal to, well, this one is only for n is equal to, this is for n is greater than or equal to 3. Because number V1 is already given, V2 is already given. So this has to be greater than or equal to 3. So this equals to just V1 magnitude plus V2 magnitude, and then plus, now we sum it from 3. This is infinity, n equals to 3, like this. 3, 5 over 6, like this. And this is from n minus 2. Alright, so we have this, and what we can do is simplify this further, because when n is equal to 3 here, so we have 3 minus 2 is equal to 1, so just replace that with n equals 1 and just put that as n. So this equals 2, and, and we know that V1 magnitude is 2, plus V2 magnitude is 3, so then this becomes summation, just make it simplified, n equals to 1, and now we have 3 times it by, right here, 5 over 6 power of n, like that. So just make it simpler like that. And if we notice, this is actually a geometric series, but the geometric series typically deal with n minus 2, so what we could do is just take this out right here. So this whole thing, this equals to 3, and I'm going to take out a 5 over 6. So we're going to take out a 5 over 6. Again, it's power of 1. Just take it out. And then, so we're going to have now multiplied by 5 over 6, power of n minus 1. Like that. And then multiply this inside here. This would just cancel. It would be 5 over 2. So this equals to 2 plus 3 is 5, plus summation from n equals 1 to infinity is going to be 3 divided by 6 is be 1/2. And so 5 over 2 times it by 5 over 6 n minus 1. And this is just a geometric series. So this right here is a geometric series, and where a is equal to 5 over 2, and R is equal to 5 over 6. Alright, so now we have this, and we can just apply the geometric series sum. Move this dot like that out. So I just moved it around. So this equals 2, and this is going to be 5 plus, remember, it's just 1, it's just going to be A divided by 1 minus R. So A is 5 over 2, divided by 1 minus R, and R is 5 over 6. Multiply the top and bottom of this one by 6. So same common denominator. What we end up having is 5, and this is 6 minus, this is going to be 5 over 2 like that. And this is 6 minus 5 is 1, and then it's denominator, flip it over to the top, like that. So this equals 2, and yeah, this is actually the other side right here. Move it over. This is 5 plus this right here. Yeah, so 5 plus that. And this would cancel out, this would be 3. So we're going to be left with equals to, this equals to 5 plus 15, and this all equals to 20. Like that. So the sum is 20. That's a pretty epic stuff. Like that. And this is the sum right here. So I'll put that in here. Summation n equals to 1 up to infinity of the magnitude Vn vector, like that. Alright, and now, so this is geometric series, so just recap quickly. So that's our answer, the sum is 20. So recall the sum of the geometric series formula that I used. Here's from my earlier video, and there's a thumbnail that includes the p-series. But anyways, this thumbnail right there. So the sum from n equals 1 to infinity of a, r, n to the negative 1. That's why we converted it into negative 1, just to deal with this right here with the formula we already have, is equals to a plus ar2, etc. Keeps going on. And the sum is equal to a divided by 1 minus r if the absolute value of r is less than 1. In our case, 5 over 6 is less than 1. Less than 1, like that. So that's our absolute value is less than 1, and then we can sum it up, and there's geometric series. How it looks like geometrically, like that. Alright, and now I quickly paused the video and updated the thumbnail to include this little part right here. And that's actually a similar triangles equation there. And just to go over the geometric series, why it works, or just to geometrically view it. So in my earlier video, I proved that this was the sum, a divided by a 1 minus r. And then you can just see this geometrically. So you have a plus ar squared plus ar cubed. It goes to, it gets smaller and smaller because absolute value of r is less than 1. So you're multiplying each time to get a smaller number. So that's the full sum. That's the sum S right here. And then it turns out, well, geometrically, if you look at it, you could form a cube right here, like that. And this cube is at A, this one is at AR, and so on. The next one's going to be AR squared, AR cubed, and so on. But then the first one, if you take a look at it, there's A, and then this one's AR, so you can subtract it A minus R. And then finally, what we could notice right here is, well, this is just a similar triangle right here. This has an angle theta. This is a straight line all the way across here. This is theta. So geometrically, this is actually the exact same thing here as we proved here. And it turns out, yeah, that is exactly, it's approaching the same triangle. So that's angle theta. And you could see that by using similar triangles. So if we look at from this angle, so similar triangles will go this adjacent over opposite, so S over A. This has to equal to this right here. In other words, the tangent. Yeah, I mean, this is the adjacent, I think this is cotangent. Yeah, this is the cotangent. It's going to be exactly the same thing. So so that's opposite, I mean, adjacent over opposite. That's S over A. Has to equal, because it's the same triangle, the same angle with the triangle has to equal to adjacent on this side over opposite. So we have this right here. And you can cancel out all the A's, just move the A across here, cancel all these out. You get this one right here. That's our S. So that's, again, as a quick rundown on that. All right, so I just want to review that. Just pretty epic stuff there. Anyways, and now the next part is, now let's take a look at problem 6. And this is looking at a largest sphere in a sphere. So it's a sphere within a sphere. So it's going to be quite epic stuff there. So Alright, in this question we're asked, find an equation of the largest sphere that passes through the point -1 and 1 and 4, or negative 1, 1, 4, and is such that each of the points x, y, and z inside the sphere satisfies the condition x squared plus y squared plus z squared is less than 136 plus 2 times x plus 2y plus 3z. Alright, so now let's take a look at the solution. So to grasp what this is asking, exactly, because this is a sphere equation right here. This is going to be the radius, but now we have these x, y, and z terms. But if we complete the square, that just means that the origin of the sphere is shifted. So let's complete all the squares first. There's a link to my earlier video, but basically it's pretty straightforward. I'm going to write this all down. So we have x squared plus y squared plus z squared is less than 136 plus 2x plus 2y plus 3z, like that. Alright, so now the next setup is I'm going to move over everything to the other side. So I'm going to move all these to the other side, this, etc., this, and separately, and look at them separately. So what we have is, yes, we're going to have, we're going to go like this. We're going to go x squared minus 2x, so we multiply 2 inside, and then we'll have plus y squared minus 4y, and then we're going to have plus z squared, and then it's going to be 6x. Z squared minus 6x, 6z. And then this is going to be less than 136. Like that. Alright, so now we have this. Let's complete the square for each one. So let's do the x one first. So that's this right here. So we'll simplify it. What I mean by that, completing the square, recall, this just means, let's say we want it in this form, x minus a squared. So x minus a squared, this would equal to, let's go, just FOIL this out. So x times x squared, is x squared. X times negative a, x times, negative a. Or just, x times minus a is just going to be negative ax. And then now we do this one, multiply this out by that itself, by x and itself. So FOIL it out. So negative a times x is just going to be negative ax. So that's the two of them. So we just add those up. And then lastly, negative a times negative a is going to be plus a squared. Alright, so basically we want this to match up with this part right there. So in other words, it has to equal to x squared minus 2x. And to do that, well, a is just 1. A is 1. A equals to 1. So in other words, this is going to be plus 1 squared is just 1. So now we can move this over to the other side. So move this over to the other side. And then what we end up having is we're going to get x squared. Yeah, so x squared minus 2x equals to x minus a squared minus 1. So that is this part here. So we can replace it with this square. And now we've gotten rid of the x, and one of the x's we put it inside the square. Now this is the origin, and this is a. I mean, this is a is 1. So a is 1. Yeah. So basically, the sphere is going to be shifted to the x equals 1. So when you plug in 1, it goes to the origin 0. So so that is at the origin is at shifted by 1. So that's that one. So the next one is going to be this part right here. So y squared minus 2 minus 4y. So we'll complete the square for this one. So it's going to be y minus a squared. This equals to, again, the same thing as over here. This can be y squared minus 2ay plus a squared. And in this case, this has to equal to y squared minus 4y. So this is going to equal to y squared minus 4y. So in other words, a is equal to 2. A equals to 2. And then this means this is going to be 4 now. A squared is or 2 squared is 4. So then solve for this one right here. We're going to get y minus 4y equals, so when we move this over to the other side, this goes all the way to the other side. We're going to get y minus a is 2 squared, and then this is going to be minus 4. I'll just move this over to this like that, and this is going to be, so we can replace this one, replace this with this right here. Alright, so now the next one is going to be, and this is going to be this right here, the z. So again, the exact same thing, z squared minus 6z. So we're going to have z minus a squared, this equals to z squared minus 2az plus a squared, and then this has to match up, so z squared minus 6z. So in other words, a is going to be 3. So 3 times 2 is 6. So a equals to 3, like that. This is going to be 3 squared is 9, like that. And then solve for this one here. So again, take it over to the other side. We're going to get z minus 6z is equal to z minus a, which is 3, squared, minus 9. So this is that. Alright, so that's what we could do, is add these all together. So so replace them all. We're going to get right here. So this part here is going to be x squared minus 2x. That's going to be x minus 1 squared minus 1. And this other one's going to replace it with this right here, y minus 2 squared minus 4. This other one's 3, and then there's a 9. So thus we're going to have x minus, let's go right here, x minus 1 squared, and the other one, we want to put all the x and y's in the same order. So I'll move this negative 1 to the far end. So I'll put it right here, like that. The next one's going to be plus y minus 2 squared. This is y minus 2 squared. And then next is going to be, and then also put the negative 4 right here. Negative 4 like that. And this is going to be plus z minus 3, 3 squared. And this is going to be, and I'll just shift this over. This is negative 1, negative 4, negative 9. And this is going to be less than, equal to, less than 136. 136. Alright, so that is what we have. And now this part right here, we could sum these up. This is just negative 1 minus, we'll just add these all together and put a negative. So 1 plus, or negative 1 minus 4 is negative 5. Minus 9 is going to be, minus 14. So in other words, 1 plus 9 is 10, plus another 4 is 14. So 14. It's going to be negative 14. So we're going to have to add 14 to this. So 136 plus 14, that's just 150. So out of 4, it goes 140. And the next one's going to be 150. So add another 10. So this means we get x minus 1 squared plus y minus 2 squared plus z minus 3 squared. And this is going to be less than 150, like that. So this is what we have. And this is just a sphere. So this is a sphere. With radius is going to be, square root 150. Like that. And we can simplify this further. The solutions manual does. So this is the same thing as writing. We'll split these all up into multiples. So 15, the same thing as writing, 10 times 15. And then this is the same thing as writing 2 times 5. And this is the same thing as writing, this is going to be 3 times 5. So in other words, we're going to get a 2 times 3, which is a 6. Square root 6. It's going to be, we'll put that in the square root. So I'll put that right here, square root 6. And the next one is going to be 5 times 5 is squared. So I'll put it all completely just so we don't get too confused. So this is going to be something as writing, 5 times 5 is squared. The other one's 2 times 3 is 6. And this is going to be canceling out the squares. We're just going to left with 5 square root 6. So that's the radius. And here I just shifted this down here so we could put the center right here. So just center on top instead. So center like this. So center is going to be at 1, 2, and 3. So basically the negatives of every one of these. So that's the center. And the radius is over there. I'll put an equal sign instead. Alright, so the center of this sphere is at 1, 2, 3, and the radius is square root of is 5 times square root 6. All right, now that we have this, so again, this is just a sphere. This is a sphere, just fix that up. So this is a sphere which describes a set of all points x, y, and z whose distance from the point P, we'll call that P at the origin right here. We'll put a P right here. Is 1, 2, 3 is less than 5 times square root 6, or 6 power of 1/2. It's not easy to do square root in this one note thing. like that. So this is less than it, so the sphere radius is going to be less than. I'll put instead of equals, put less than. Because the radius is a set of all points less than this full sphere. Alright, and now the distance from P to Q, we'll put Q as the point we were asked, so -1, 1, and 4 is, and I'll illustrate that soon, but let's go back to the question. So the question is, find an equation of the largest sphere that passes through the point -1, 1, 4, so we'll call this Q. I'll just put call this Q, like that. And it's such that each of the points x, y, z inside the sphere satisfies a condition like this. Yeah, so we need to have a sphere that basically lines up with this, but it's also such that it's inside it satisfies this condition right here. So all these points have to be less than a actual sphere inside. Like that. So it's actually going to be a subset of a sphere inside a sphere. All right. So now go back to that drawing right here. So we have this right here. So we need to find out the distance from here to here. This is what we're getting. The next part is this is P, this is Q. So finding the center. This is from Q to P. All right, so this is distance from P to Q is, and we could just basically use the 3D geometric formula for it, and as it's going to be again, as an earlier question went over it. So PQ, the distance or the absolute value sign like that, is going to be equal to, and here we just subtract each term. So we'll just go P to Q. So -1, or I'll go 1 minus -1. So 1 minus -1 is going to be +1 squared. And then 2 minus 1 is going to be, oh, why is it doing that? Okay. Yeah, this is going to be plus, I just fixed that up. This is going to be 2, minus 1 squared, and then the next one's going to be 3 minus 4. And then all squared. Yeah, so this equals to square root 2 squared plus, and then this is going to be 1 squared, plus this is going to be 3 minus 1. It's going to be -1 squared. I'll just get rid of these pluses. Do it all right away. So 1 plus 1 is 2 squared. That's 2 squared is 4. And the next one's 2 minus 1 is 1. Squared is 1. -3 minus 4 is -1 squared. It's going to be plus. It's going to be 1. So this equals to square root 6. All right. So that's the distance from P to Q. Yeah, so thus the largest possible sphere that passes through Q and satisfies the stated conditions extends 5 times square root 6 units in the opposite direction, giving a diameter of 6 times square root 6 as in the diagram below. Alright, so here let's have a circle. Here's just a placeholder. We'll modify it in a bit. So what we have is, let's say we have the point Q right here. Let's say we have Q here is going to be this right here is Q. This is at -1, 1, and 4. Just double check that. Yeah, so -1, 1, and 4 right there. And the distance from that to P, so P is going to be somewhere across to there. Yeah, I'll put a line like this. This is P. And this is, I'll write this as P. It says 1, 2, 3. And basically it's like this. So 2, this is -1. It's going to be, let's just shift it to the right. By 1. Yeah, by 2 units. The next one is a bit down, and I'll just put a random point like that. Anyways, so that is our point P. But I'll do this like this. All right. So we have this. All right, and this is a point P like this. So that's P. Actually, I'll put it better like this. And now this distance is square root 6. So that's square root 6, like that. Alright, so let's move it down here. So if this is the point P, and this is distance square root 6 from Q, and we have the condition that, basically the condition is such that this right here, so every point inside the sphere has to satisfy this condition. So in other words, it has to be less than a sphere of radius 5 times square root 6. So in other words, every one of these points has to be less than a distance, and we'll draw this all the way across here, less than all the way up to here, and this is going to be 5 over 6. Yeah, this is 5 over 6. Like I mean 5 times square root 6, not 5 over 6. 5 times square root 6. Let's move that dot away. 5 times square root 6, like that. So in other words, this is a sphere, the condition. So I'll put this right here. So we start from here. And this sphere is actually what we're trying to solve. This actually goes up to here. And let's just move this all the way back. So we have a sphere like this. And this is what we want to find. So we're finding the largest possible sphere that passes through Q. So passing through Q and satisfies the conditions that's going to be less than basically the farthest distance right there. It has to be within the other sphere of the radius 5 times square root 6. So in other words, this right here, and if this is, so basically what we want to do is find the center. So we want to find, what I'm going to do is put this 5 over 6 like this. 5 square root 6, because we want to know the center of the sphere. This is what we want to find. But we also have another sphere, just to illustrate the big sphere is a condition it needs to solve. So basically a sphere within a sphere. This is going to be right here. But then the center of this is going to be extend all the way until the center is at P. And to get this exact sphere there, I'm going to take this. This is the radius of the center P. I'll move this like this. I'll move it all the way here. So move it right here, and we'll rotate it all the way. Actually, I'll rotate it like this. Let's rotate it like this, so it's exactly the same length. So that's the diameter. Yeah, so it's pretty much, we almost got it exactly it. So let's get back to our sphere. This right here, move it a tiny bit bigger. Okay, move it like that, and exactly that. Yeah, so that is at that point P, and this is also square root, this is radius also. Like that. And this is, I'm going to call this point right here C. And this is 5 square root 6, and this is also 5 square root 6. This is also, I'll put a light like that. This is also 5 square root 6, like that. All right, now here I just move this over here. So thus the desired radius of the radius of the desired sphere is 3 times square root 6. Actually, I forgot to get over that, but basically we can solve this because this full distance right here is square root 6. It's 5 over 6. So I'll move this actually over here, and then this is from here to here is just so it's you can see it better. This is square root 6. So in other words, the r right here. So this is the one we want. It's called, yeah, so this r is going to be equal to, well, the full diameter is going to be square root 6 plus 5 square root 6 all divided by 2. So in other words, add those up, we'll get 6 over square root 6 over 2. Like that. This is just going to equal to 3 square root 6. Like that. So that's our desired radius. So that's our desired radius. And we know the equation of the big sphere, and we know that Q is a distance square root 6 from the center of the big sphere. So we can calculate the equation of this smaller sphere. All right, so let's continue further. So basically, thus the radius of the desired sphere is 3 times square root 6, and its center is 3 times square root 6 units from Q in the direction of P. So it's going down here like that. So we could use a unit vector in this direction, but first recall unit vectors. Recall from earlier video. It's a link to it and the thumbnail. So unit vector right here. If you have a vector right here, A, like that, this is A. Unit vector is just a length 1. And it's in the same direction as it, so it's parallel to this one. So it's exactly on it. It's a unit vector, and the unit vector you can calculate just by taking the vector A divided by the length of A. So that the unit vector absolute value of its length is just 1. So that's all a unit vector is. So thus a unit vector in the direction of from Q to P is, so we go from Q all the way to P. Let's just draw these all out. So we have Q right here, and now it's going to go, this is P right here. So unit vector is going to be right over here. I'll call this U, and again, we know this length is square root 6. So then the unit vector in that direction is going to be equal to, well, we got to get the full position vector right here. I'm going to put right here, this is from here to here. The full one is QP. Or actually, we already have I'm going to put an arrow right here. So we already have QP right there as a vector, the full one. This is the full one. I'm just going to put Q, QP like this. Whoops, Q, P, put an arrow. So this is equals to basically QP divided by the length. And the length is going to be, let's put it for completeness, QP like this, position vector. This equals to, this one here we just subtract 2, so P minus Q. And P is 1, 2, 3. So we're going to get 1 minus, and then this other one is, Q is, we know Q is negative 1, 1, and 4. So this is going to be minus negative 1, so it's going to be plus 2. Plus 1. And then, and this is in vector format like this. And we already solved the other one. Yeah, so P is going to be 2 minus 1 is 1. I'm just going to go put 2 minus 1 just for completeness. And the next one is 3 minus 4. Like that. Like this. And this whole thing is divided by square root 6. So in other words, this is going to be 1 over square root 6. And then this is going to be 2, 1, negative 1. Like that. So that is our direction vector along the direction from Q to P. Alright, so now if we extend further out, all the way to C, so this is up to C, and what I'm going to call this vector from Q all the way to C as QC. So basically, like this to this is QC, and its length is just we already know this one. The length from Q to C is the radius, so it's going to be 3 times square root 6. So this is going to be, it's going to be 3 square root 6, like that. Yeah, so then QC, we can solve QC, because remember, QC is just this direction vector like that, so we just, if it's always 1, so this QC is just going to be equal to, always multiplied by the position vector. So we just go to QP, actually, not QP, we just multiply by the position vector and the length. Because this is just length 1, so we just multiply by the full length. So in other words, we get 3 square root 6 times by U position vector. This equals 2 because it's all along the same line there, same direction. So this equals 2. So what I'm going to do is multiply this inside there. So this is going to be, I'll put this like this, 3 square root 6 over square root 6, and then this is, just put that in here, 2, 1, negative 1. Like this, and then this would cancel, and then move 3 inside. So this equals 2, 6, 1. 6, 3, negative 3. Like this, 6, 3, negative 3. Like that. All right. So this is the position vector of QC. But to get the actual point C, we just have to combine these two vectors right here. We go Q plus this right here. Yeah, so basically to get the center, so thus, the center or a center as a position vector pointing basically to this, like that, as a vector, from the origin. Again, as vector, origin, point, same thing in this scenario because the origin is 0, 0s. This is just going to be, and again, this center right here is this part right here. So we want to know this. We know the position vector like that. I'm going to draw it actually for completeness. Yeah, so move it over there. So thus, what we have is, if we have C like this, we know this position vector, this is QC like this, and we also know from here to here, this is just from to Q. And that's just the point Q as a vector. So then C is equal to the combination of all these things right here. Thus, C equals to Q plus QC, and this equals to, well, Q is negative 1, I think it's 1 and 3. Let's see if we got that right. Yeah, so Q is, I think we have, Q is 1, negative 1, and 3. Negative 1, 1, and 4. So that's Q. So negative 1, 1, and 4. And then plus QC is just the top one there, 6, 3, negative 3. Like that. This equals 2. So negative 1 plus 6 is going to be, well, 6 minus 1 is going to be 5. Then 1 plus 3 is 4. And 4 minus 3 is 1. So then the center is just, the center is at 5, 4, and 1. Yeah, so that's what we get is a sphere. And we know the center and we know the radius. So our equation for when we're asked to find the maximum sphere, the largest sphere we can find is, well, x minus 5 is the center, 5 plus y minus 4 squared, and then plus, actually, it's all plus for a sphere. This is going to be plus, this is going to be z minus 1 squared, and this is going to be equals to, this is the largest sphere that we can possibly do, this equals to the radius squared, so 3 times square root 6 squared. Alright, so we have the origin, we have this all, and this one is just 3 squared is 9, so this is just going to be 9 times 6, the 6 cancels, the square root cancels, so 9 times 6 is equals to 54. So we could just copy and paste this and equate it all. Yes, move it down here, so then this equals to, yeah, this equals to right here, equals to 54, like that. And yeah, this is the largest sphere under the conditions of the question, and just to double check it all, we're going to see it visually. We can graph this using GeoGebra's 3D graphing calculator. There's the link there, and this is our point P, or point Q, P, and C. And there's a sphere right here. Basically, you can create an equation. There's a sphere of Q with center C, radius 3 times square root 6, and it gets you exactly our answer. So x negative 5 and y minus 4 as z minus 1. And then the sphere, the one where we had the 151, is negative 1, 2, and 3, and 150 there. And you just put the point P, and does it. So it automatically does it, and there it is. So we have a sphere. This is in a bluish area in the center. There's all our points there, and we can see them all visually. So there it is, and we can move this around. So we can move this around in 3D, and let's hide the big sphere. There's our small spheres. There's the point Q. There's our point Q right there, and this is, yeah, so the point Q is at the negative 1, so it's in the back. The x is negative 1, so in the back over there. There's our point P in the center. I'm going to hide the sphere. Yeah, there's how it looks like. So there it is. There's Q, there's P, there's C, and again, if you have this one right here, this is the sphere right here with a radius 3 times square root 6, or square root 54. So that's how it is. And then you have the big giant one, completely exactly on the edge. You could try to zoom in. It's exactly on that edge there. Yeah, it's exactly on. It's actually epic. Let's go back here. Yeah, so it's exactly on that edge. So epic stuff here. I'm just going to zoom out. Okay, so zoom out, move it around, and yeah, right on the edge. So that's amazing stuff. Alright, so that is quite fascinating. Alright, and now let's move on to problem 7, and this looks at a block on an inclined plane. So this question we're asked, suppose a block of mass m is placed on an inclined plane as shown in the figure below. So there is the plane right here, has the weight W, so it's mass times gravity. And this is the this force right here is a force due to friction that's dragging it along here, and there's the normal force perpendicular to the weight there. I mean perpendicular to the plane. So the force of friction depends on the normal force right there, which is right this, yeah, which is perpendicular to this plane right there. And basically, the flatter this is, the higher the normal force and higher the friction. So the block's descent down the plane is slowed by friction. If theta is not too large, friction will prevent the block from moving at all. So there's a theta right there. So if this is not too large, it will be held up by friction. So the forces acting on the block are the weight W, where the magnitude of the weight is equal to mg, where this equals to basically the magnitude is just mg, like that. Where g is the acceleration due to gravity, and the normal force n, or the normal component of the reactionary force of the plane on the block, is basically the plane is pushing back opposite of the weight on, this is a normal component to it, that's pushing back upwards on there. And this is the normal component of the reactionary force of the plane on the block. And again, reactionary force, because if you just have a regular block like this on just a flat plane like this, the weight is being held up by an equal reaction force. So N, in this case, equals to W. If this is W, it's not moving. So that's a perpendicular one, but this one, it does not equal it necessarily because, yeah, this is not going to be equal to it. It's at an angle, and so on. And here where the absolute value of N, or this the magnitude of it, the normal component of the reactionary force of the... Actually, no, I think I typed that in. duplicate. Anyways, erase that. So where the magnitude of N is equal to just lowercase n. So this is the magnitude of it, like that. So this is absolute value is equal to N. Like that, alright? And the force F due to friction, which acts parallel to the inclined plane opposing the direction of the motion. Alright, so now if the block is at rest and theta is increased, the absolute value of here must also increase until ultimately, so the absolute value of F, the friction force must increase until ultimately the friction force reaches its maximum, right here. Beyond which the block begins to slide. For example, if you have initially right here, here's a block on a flat plane, this is all normal force is equal to W, and this is W, and it's not going to move anywhere, and also there's friction here is 0. The friction force is 0, and then as you increase it, you're going to slowly increase friction until a maximum value, after which it starts sliding. So you could play around with a block on a plane like that on your own, and you'll see just that. Alright, so at this angle, we'll call this theta sliding, or theta s, so I'll just ignore this correction. It has been observed that the absolute value of F is proportional to N. So at this angle, this right here, the sliding angle of theta s is going to be proportional just at the moment where it begins to slide, or just a moment before it begins to slide. Anything higher, it will slide, and that is proportional to N. So thus, when the friction force is maximal, we can say that friction is equal to we'll call this this is a mu, actually. I think it's Greek for mu right there. So mu of s, like that, times it by n. So just proportionality constant. So where mu I think that's a Greek or Latin or something. Let's see what I wrote here. Yeah, so here's quickly on Wikipedia. So mu is written like that, lowercase. Mu is the 12th letter of the Greek alphabet. Alright, so mu. So we're using some Greek right there, and that says Greek is mu. Alright, so epic stuff there. And this coefficient is called the coefficient of static friction and depends on the materials that are in contact. Alright, so now we have 3 questions, or 4 questions here. I'm just going to read the first one. We'll solve the first one, and then we'll solve each one separately instead of reading it all out, just because it's a lot of questions. So part A, observe that n, the vectors n plus f plus w equals 0, and deduce that the sliding friction right here, this is at the sliding. And this is just before the point of sliding. And deduce that the mu of s is equal to tan of theta of s. Alright, so basically it equals to the tangent of that angle there. Alright, so let's take a look at that. So let's go look at the solution to part A. So when theta equals to theta s, or the theta sliding, the block is not moving, because anything higher then it will move. So the sum of the forces on the block must be 0, thus the sum of n plus f plus w equals to 0. And yeah, this relationship is illustrated geometrically in the figure below. First of all, basically, if it's not moving, then again, we're going to have n plus f plus w equals to 0. And this is all vectors like that. And if we rearrange this, we're going to get, just make it in terms of n plus f, like this. So what we get is n plus f, normal force with the friction, plus the friction force equals to negative w, f, like this. And this is theta s. I'll put theta s right there. And now we can see this geometrically. I'll draw this as this summation right here. So n, so what I'm going to do is like this. This is the flat line like that. I'm going to draw f this way. So there's the sliding one. I'm going to parallel to this f there. So this is our f. I'll write it a bit lower, like that. And this angle is theta s, like that. All right, so f plus n, and n is the normal force, is going to be like this. It's going to go straight over to here, and this is our normal force, n. And now we have the w is going down like this. So in other words, w is going negative down like that. So this is how it looks like geometrically, because you'll have n plus f plus n, so if you do the vector summation, it equals to w, but it's going backwards, so it's equals to negative w. And now if we take a look at the angles right here, this angle from the bottom, this is a right angle from here. I'll draw this. So this is right angles. This is right angle and also right angle this way. And so in other words, this is 90 minus theta s. So then this angle right here, this is actually going to equal to theta s. And you could see this because this is a triangle. So recall the triangle is at 180 degrees. So minus all the angles inside. So 180 degrees minus 90, or minus this 90 first, minus 90. And then minus this 90. 90 minus theta s, like that. So then this becomes, well, this is 180. 90 minus 90 is negative 180. So these all cancel. This is equals to theta s. And also you could see that this is, if I just extend this out to there, yeah, if I just extend it out like there, this is going to be right angle right here. And this is going to be, it's going to be 180 minus 90 minus theta. So it's going to be another 90 in there. 90 minus theta right here. So again, it's just exactly symmetric. 90 minus theta s, like that, and so on. So that's what we get. Yeah, so if it's 90 minus theta here, this has to be theta, this is theta s. So this is 90 minus theta s, this can be theta s. So in other words, we do this because we see it's a similar triangle. I mean, not a similar triangle, just we use a tangent. So if we look right here, we have this triangle W, N, and F. So we can just write this out as thus, tan of theta s is equal to opposite, which is f, over adjacent. Adjacent is a normal vector n, like that. So opposite is f. And yeah, so opposite is f right here, and the other one is the adjacent. So then this equals to, this equals to number f is just equal to proportional to the normal vector value, so n, like this. And yeah, actually, since we're dealing with the magnitudes, so we're taking the magnitudes of this, not just the vector. So this tan theta of s, and if you look at the magnitudes, magnitude of the friction forces is mu s, mu sub s times n, and then this one is just n. So this cancels, and we're just left with, I'll write this better, mu of s equals to tan theta s. So there it is. Alright, so yeah, and that is pretty much it. That's our tan theta s. That is what we were asked to solve right here. And that's correct. So now let's take a look at part B. In part B, we're asked, suppose that for theta is greater than theta s, an additional outside force H is applied. So now, even though it's above it, so it's going to be sliding, there is an H above it applied to the block horizontally from the left. So we're going to apply a value of like this, and it's going to be, the magnitude is going to be lowercase h right there from the left, and let the magnitude of capital H vector equals to lowercase h. And if h is small, the block may slide down the plane. If h is large enough, the block will move up the plane. So if it's really big, it will start sliding upward. But if it's not enough, if it's small, it will go down. So you got to go just right. So let h minimum be the smallest value of h that allows the block to remain motionless. So it's always dealing with the not moving case. So that so that the force right here, the friction force is maximal. So the friction force is max, such that it's going to slide if it's anything more. But now we're doing a tiny bit of force just so it doesn't move. And this is just at the maximal right here. So basically, look at the minimum. We got to push it. So by choosing the coordinate axis so that the force F lies along the x-axis, resolve each force into components parallel and perpendicular to the inclined plane, and show show that these equations are all true. So h minimum times sine theta plus mg cosine theta equals n, and h minimum times cosine theta plus mu sub s times n equals mg sine theta. So in other words, this is saying choosing the coordinate system so that f lies along the x-axis. So in other words, we have to rotate this down. So this is along there, but the x-axis is over here. So we need to rotate this down by, well, theta. So that we'll have x along that parallel to it. So let's take a look at that. All right, so let's take a look at the solution, and then basically we have to resolve each force into components parallel and perpendicular to the inclined plane. So we got to resolve everything parallel and perpendicular, like that. So let's just rotate it and see what happens. All right, so let's take a look at the solution to B. So we place the block at the origin and sketch the force vectors acting on the block, including the additional horizontal force H, with initial points at the origin. We then rotate the system so that that F lies along the positive x-axis and the inclined plane is parallel to the x-axis as in the following figure. Alright, so let's draw the origin. Alright, so initially we have, here's the origin. I'm going to go dash lines. Actually, before we do dash line, I'm going to go, there's a horizontal, we're going to put everything at the origin. So this is our H right here. This is our horizontal, and then there is the dash lines for the x-axis there. So sketch the force vectors along. So we place the block at the origin. So it's going to be at the origin, and sketch the force vectors on it, and including the additional horizontal H. So it's like that, and now we have the friction force is up like here, and this is our angle theta, and this is going to be a force vector like this. And now we have a normal force like this. And this is perpendicular to that. And then again, we have to draw the vertical axis like that. And now we have a W going down like this. This is our W. And that's our weight like that. But now we're going to rotate it. So we're going to rotate everything by theta so that the F is horizontal. So what we're going to get is here's the origin. This is our F. And this is our new horizontal setup there. And so that means that H is going to be rotating by theta, so then H is going to be down like that at an angle theta, and this is our H. And this also means that, well, we have here rotating everything, so then the W is going to be going over all the way to here. Also, this W is make it a bit more realistic, so it's a bit longer. Let's go. It should be the biggest one, I think. Oops, I don't know why it does that sometimes. Now let's try that again. Okay, so this should be the biggest one, W, like that. All right, and then this one should be slightly smaller, just because the normal reaction one is going to be, the friction force is the third biggest. That's going to be our N, like that. All right, here I just fixed that up, made F a tiny bit smaller, and so on. So now what we're going to have is W. This is the W like this. I think we already have, yeah, let's erase this. Put a W like that. All right, so now this is going to be, W is going to be over to here, and this is angle theta. And now the normal force, because it's perpendicular to this, is going to be just vertical upwards like this. So that is our normal force. Make it a bit taller. Okay, it's good enough. And this is going to be our normal force, and this is perpendicular to this. All right, so going further, we're given that the angle is higher than the sliding angle, so that means that the absolute value of F, the friction force, is maximal, so that F is going to be, the magnitude is going to be mu sub S times N, for N is greater than or equal to theta S, because it's at the maximum. So it's not going to get any more based on the material, because when you get a higher and higher angle, eventually you're going to get a vertical like this. You're going to have zero friction. But yeah, actually, because we're increasing it such that it's already at maximum like this, and let's say the maximum's over here, but now we're going slightly over there, so you're still going to have some friction force as long as you have some some normal force there. So anyways, it's if you think about it again, I think it's going to be near this sliding one, but it's more than, but still it's a maximal. So anything higher is going to be sliding. So it should be sliding, but we're adding a horizontal force to it. So then the vectors in E in terms of components parallel and perpendicular to the inclined plane are, so we're going to have, so in this case right here in terms of this, we're going to have, and this is our W, so we're going to do it in terms of, this is our new coordinate system. So the J component is at the top right here. This is our J, and then this is our I component, or X component. Because we're dealing with vectors, put IJ, like that. Like that, okay. So then that means the N, let's do the normal vector like there. The normal vector is going to equal to, this is going to be equal to just lowercase n. So this is just at the maximum. So we're going to go nj like that. And all right, and yeah, that's the absolute value of or just the magnitude of the normal vectors n, and it's going to be in this component. I'm going to write this in vector form like this. It's going to be basically 0 on the i's component, and now the j1, just put n like that. And then likewise, the next one is going to be f like this. This equals 2. This is just horizontal, perfectly on the positive I-axis, or the positive x-axis. That's just going to be mu sub s times n, this I component. Or in vector component form, this is written as mu of s n and 0. Alright, so now the next one is going to be w, and w is right here. So this one, this is going to equal 2. Well, we have a angle there, so then we need to go to the horizontal one is going to be on this sine side, like here. It's going to be the sine of the angle times the magnitude. So this equals 2. Yeah, it's equal to, and it's also on the negative side. So this is going to be, actually, the negative side is going to be negative. The magnitude is mg, and then times it by sine theta. So sine theta is opposite over a hypotenuse, so we get the horizontal one right here. So that is going to be this one right here, and that's going to be our I. And then plus, the next one is going to be, the vertical one is also going to be negative mg, and then this is going to be cosine. Negative mg and cosine theta j, like that. And we could write this in component form, but I'm just going to keep it as this because it's too long to add all that. So now the next one is, yeah, the h. We forgot to add the h right here. So this is the last one, is our h component, and this is going to be, this equals to, now it's going to be, in this case, the cosine, and it's going to be positive, the cosine of this angle there. So that is going to, because the cosine is adjacent, so we're going to have cosine angle. Yeah, cosine angle, and it's also, whenever we were told the absolute value of h is just h min. So we're going to go the minimum like that. All right, just put a bracket around that. That's going to be our I, like that. So h min bracket cosine. And then plus, the next one is going to be, it's going to be on the negative side, and it's not loading. Okay, so negative, and then sine. So sine to get the opposite, and then the h min. So h min sine theta, and then j. And it's a negative, because we're going downwards there according to our axis. And now the next setup is, well, we just equate components and see what we get. Well, let's equate the, let's do the I component first. So equate the I component. We're going to get, basically sum all these up. So 0, yeah, so, and it's not moving, so we're going to go 0 plus mu sub s n plus, and then it's going to be, well, negative mg. Let's put a negative mg. Negative mg sine theta, and then plus hm minimum cosine theta. This equate this equals to 0. So because it's not moving, so everything equals to 0 like that. Yeah, so what I am going to do here is I'm going to put this h min first. I'm going to put h min like this, cosine theta, and plus mu sub s of n, and I'm going to move this over to the other side. Put it all the way to the end, so we're going to get equals to mg sine theta. And the reason I'm doing this is that's exactly how the question we were asked to do. And I'm going to box this in. So this is the first equating. This I'm going to call this equation 1. So mg sine theta. So this is h min cosine theta plus mu sub s times n. I'll block this out. Like this, mu sub s times n, and then mg sine theta. So if we go back up to the question we're asked, part B, h is the first one, h min sine theta plus mg, actually this is the second one. So h min cosine theta plus mu sub s and mg sine theta. So this is correct. I don't know why it doesn't just let me, sometimes that, right, okay, this should be working. So h min cosine theta plus mu s and mg sine theta. So that is right here, h min cosine theta plus mu s and mg sine theta. That's our first equation. So now the next one is the j component. Okay. So let's do a look at the j component. Let's write this a bit better. All right, so the j component, we combine all these ones there. So what we're left with, this is going to be n. Okay, so n plus 0. Just put everything for completeness. Then plus, this is negative mg cosine theta. We'll put this like this, minus mg cosine theta, and then minus hm sine theta. Hm or h minimum sine theta, and this all equals 0. This is not moving. Alright, so what I'll do is now I'll move these all to the other side, and then write n on the other side as well. So move this over there, and then write them first, so we're going to be positive. So I'll put an arrow like this. Okay, I don't know what is happening anymore. Yeah, my OneNote just glitching out. Okay, so we have this. It's going to be mg cosine theta plus h min. It's plus h min sine theta. And what I'll do is I'll rearrange it. Here, I quickly just rearrange this, pause it, and rearrange it, just so we'll have this in front, this one after, just because that's what the question is, and then put the n at the end there. So this is what we have. All right, so we have this, and I'll call this equation 2. And now if we scroll back up, I'll write this h a bit better, like this. So h min, if we scroll back up, is exactly what we were asked to solve. So h, this is b. This is the first equation. H min sine theta plus mg cosine theta equals n. So h min sine theta. So h min sine theta plus mg cosine theta equals n. So that is that. Yeah. So that is that. And that's actually that is basically all we're asked to do in question or part B. So now let's look at part solution to C. Yeah, so let's take a look at the question C first before we get to the solution. So part C says, show that h min equals to mg tan theta minus theta s. And then we're asked, does this equation seem reasonable and doesn't make sense for theta equals theta s? And what about as theta is approaching 90 degrees? Explain. All right, so it's a big question there. So let's take a look at this. We got to find out. We got to find out what h min is. Basically, we got to solve for h min. So, and we have h min in both these equations. So, since equation 2 is solved for n, so it's already solved for n, we can substitute it into equation 1. So we can just basically throw this n all the way inside there and then solve it. So let's just take a look at that. So let's look at this equation 1. So we'll have h min cosine theta, so that's this right here, plus mu sub s, and then n, and n is going to be, well, h min times it by sine theta plus mg cosine theta, and then this is going to equal to equals to mg sine theta. Mg sine theta, and I'll just put a dot there so it looks like that. So mg sine theta, and so on. All right, so now we can just rearrange and solve for it. All right, so now we just simplify this further. So this is going to be equal to h min cosine theta, and then plus, I'll write this as mu sub s h min, and then sine theta. And then the next one here is going to be plus mu sub s mg cosine theta, but I'm going to move it over to this side because there's no hm there. So this equals to mg sine theta, and then minus by this and this together. Just multiply that out and minus it. So that equals to mu sub s mg cosine theta. All right, so what we end up having is, well, let's take out the hm here. And so what I'll do is hm, or h minimum, is going to equal to cosine theta plus mu sub s of sine theta. This equals to, and take out the mg, and this is going to be sine theta minus mu sub s cosine theta. Alright, so thus hm is equal to, or h minimum is equal to, just divide this out, move it over to the other side. So what we end up having is mg, let's put the mg by itself, and we got this equals to, I don't know why it's not writing, okay, mg, then we have a giant equation right here. We're going to have on the top sine theta minus mu sub s, write this a bit neater. This is sine, and then this is mu sub s cosine theta, and then I'll divide this by cosine theta plus mu sub s sine theta. Now this resembles a trigonometric identity, and to do that, this actually resembles a tangent one, and to do that, we're going to multiply top and bottom, just divide both by cosine theta. So divide top and bottom by cosine theta. So then this ends up becoming equals to mg. The top sine theta is going to be divided by cosine theta. That's just tan theta by definition. So I'll just make a bigger bracket right here. Tan theta, and then minus mu sub s, and then a cosine divided by cosine just cancels out. So all we have is tan theta minus mu. Alright, so we have the top part, let's fix this up a bit, negative there, and then the next one is going to be, well, divided by cosine. Again, it just simplifies it when you divide by the cosine out, and this is going to be equals to 1, and then plus mu sub s, sine theta over cosine theta, again, that's just tan theta by definition, like that. And now, we'll recall, and I'm going to put recall that because F, the friction force at a maximum, the mu sub s, the coefficient of static friction, is going to be equals to maximum as well. It's going to be tan sliding one, tan of theta s, or theta sliding. So I'll box this out like this. And so we can just throw this back inside there. So I'll put a recall like that. Erase that. Alright, so then this ends up equaling to mg tan, this is going to be tan of theta minus, this is going to be tan of theta s. And the bottom one is going to be a bit bigger. 1 plus tan of theta s, tan of theta, like that. And now this is actually a trigonometric identity. This is actually mg tan of theta minus theta s. And I'll show you that soon. So that's our h min. Like this. That's our h min over there. Alright, and that's actually our exact answer. And first of all, note the trigonometric identity I used. There's a link to my earlier video. So if we have tan of theta minus theta s, or x minus y, so two angles like that. So tan x minus tan y divided by 1 plus tan x tan y. And that's exactly what we have here. Imagine this is replaced with x and y, x and y, x and y, x and y. So that's just tan x minus y. And that's exactly what we were asked to solve. And I'll scroll up. This is, go back to part C. So part C, show that h min equals mg tan theta minus theta s. Does this equation seem reasonable? Yeah, now we're asked, does it seem reasonable? Does it make sense for, and again, this is correct, mg tan theta minus theta s. Does it make sense for theta equals theta s? What about as a theta approaches 90 degrees? Explain. So let's take a look at what I had written, or the solutions manual written. So note that for theta equals theta s, h min, h min, so if theta is equal to theta s, h min is equal to just mg tan theta. This, if these are equal, mg tan theta, that's just 0. So tan of 0 is 0. So which makes sense since the block is at rest for theta s, thus no additional force for force h is necessary to prevent it from moving. So that's just the friction alone will hold it in place. As theta increases, the factor, this is theta minus theta s, and hence the value of h min, so this right here, will be increasing slowly. Increases slowly for small values of theta minus theta s, but much more rapidly as theta minus theta s, as theta minus theta s becomes significant. And you can see how the graph for tan is. So if we have the graph of tan like this, I'll look at this. So imagine you have theta minus theta s. This is our tangent of it. What ends up happening is it's an exponential like this. It's an exponential like this. and this is at 90 degrees. This is at 90 degrees right there, and also on the reverse side, when we're dealing with negatives, it goes negative like that. This is negative 90. But we're only dealing with positive because of the angle of the real world application here. So then it goes slowly and then goes rapidly up. And this seems reasonable. And I'll go here. This seems reasonable because as the steeper the inclined plane, the less the horizontal components of the various forces affect the movement of the block. Because again, if it's almost 90 degrees, you're pretty much vertical like here. This is the friction one's gonna be 0. So you're gonna need a whole lot of force. You're gonna have pretty much going to infinity there. And that's because that's assuming the friction force is already maxed out, so you can't get any higher. Yeah, so this seems reasonable. As the steeper the inclined plane, the less the horizontal components of the various forces affect the movement of the block. So we need a much larger magnitude of horizontal force to keep the block motionless. If we allow theta to approach 90 degrees, corresponding to the inclined plane being placed vertically, so again, the whole plane will be vertical. Now you have the block on it like that. The value of h-min is quite large. This is to be expected as it takes a great amount of horizontal force to keep an object from moving vertically. So you got to literally imagine a textbook. You have to force the book on the wall as hard as you can so it does not fall down. The heavier it is, the harder it is, and also the less friction on the wall, the harder it is as well. In fact, without friction, so if there was no friction, yeah, and here it says, in fact, without friction, so if theta s equals to 0, so if you have this equation in here, so if we had no friction, this h minimum, and there was nothing to equate this, so we had this just equated to 0, sliding one is 0. Yeah, so in other words, the angle at which sliding occurs, so if it can slide at a flat thing like here, any amount, so then the angle is basically flat will slide, then we would have theta as approach 90 degrees, and thus h min approaches infinity. Yeah, so then if this was 0, if this was 0, the 0 friction, sliding friction, and then this approaches 90 degrees, this is going to infinity. This goes straight to infinity, like that. So I'll just erase this. So yeah, so that does seem reasonable as well. So, and it would be impossible to keep the block from slipping, so no amount of horizontal force would be necessary, because as this goes to infinity, the h minimum goes to infinity as well. So that is that. So you're going to need a slight angle at all times for it to be pushed upwards. All right, and now let's take a look at part D. Let's just scroll up and read it. It's going to be another epic question. So let h max be the largest value of h that allows the block to remain motionless. In which direction is f heading? And and it also asks, show that h max equals mg tan theta plus theta s. This was theta minus theta s. It's going to be plus. Does this equation seem reasonable? And explain. And again, this is now, instead of the h minimum, before we had, this is what we had in part C, where we had a minimum so that it doesn't slide down. And now we're asking a maximum so that it remains, so like a giant maximum so that it doesn't move, well, in this case, for having maximum, it remains motionless. In other words, it doesn't move upwards. So just before it moves upwards, it's going to have a downwards friction force because it wants to go up. So you're going to have a friction is now going downwards. So that's a pretty interesting conundrum. So let's continue further. And also, we got to show that h max. Solve for h max and then answer or ask if it's reasonable and whatnot. So let's going back here, D. So solution to D. So since h max is the largest value of h that keeps the block from slipping, the force of friction is keeping the block from moving up the inclined plane. Thus, F is directed down the plane. Our system of forces is similar to that in part B, then except that we have the F right here is negative. Except we have that, I'll put it that. We have the friction force, so that it shows up on the bottom line. Friction force, F is equal to negative mu sub n, mu sub s times n on the I vector. So, and note that the force of friction right now is again maximal, because we're going for the maximum applied horizontal force. So then we're going to need to have a maximum force of friction. So this is going to also equal to, it's also equal to right here, mu sub s times n. On the negative side. So following our procedure in parts B and C, we can equate components. So we're going to have to reverse it again. So yeah, so let's just do the same thing. Let's try to speed it up. So we have, this is our angle. This is our inclined plane. at an angle theta. And I'll just draw this, just draw it like this. And so then this is going to be a horizontal force on it. This is going to be our H vector. It has a normal vector, N like that. It has a weight like this. And now the friction is going to be going downwards, like that. So that's the friction force. And I will draw this. Now we're going to rotate this again to get it to the inclined plane so that it's parallel to the inclined plane. So we're going to go backwards here. This is the origin. So it's going to go backwards. This is going to be our F. This is going to be dot, dot, dot. And now we have, this is going to go, so we're rotating everything. Actually, we're rotating, same thing actually. We're still rotating it the same direction. Like this, theta. So then if this is, and this is perpendicular to it, again, so this is going to be, the normal force is going to be up like that. And the weight, again, is going to be on the same thing like this. This is the weight. This is the weight like this. And this is the angle. It's going to turn like that by theta. And likewise, the horizontal force, move it over to this. Initially, it was at the center, but now rotating it. So it's going to go down like this. This is our H vector, and this is at an angle of theta. Between like that. And now just equate components. So I'll just put it all in together. So the I component, instead of doing what we did before, so I'll just put it in the I like this. So the horizontal components, just do it all instead of writing it each separately, because it's all pretty straightforward. So we're gonna have right here, the only one that's on the left is going to be negative F. So I'll put negative F, which is mu sub S times N. And then we're going to have negative the W. This is going to be negative mg. And now this is going to be sine theta. This is for the W, sine theta W. And now this one is on the right side, so it's positive. So plus is the horizontal one. Plus, and H is going to be lowercase h max. This is the maximum force. And now it's going to be cosine. So the cosine is the adjacent one, the horizontal component. And this equals to 0. So solve for this. We get H max. So H max right here, cosine theta. And what I'll do is I'll just minus mu sub S times N and move this over to the other side. So move that over to the other side. This just equals to, just make it similar to what we had in parts, I think C or something. Okay, I don't know why it's, okay, this is going to be mg sine theta. So we'll call this equation 1. And again, this is very similar to what we had earlier. Yeah, scrolling back up here. So it's basically the same thing, but now we have h min cosine theta, and then minus mu sub S times N, and this the right side's mg sine N. So basically the exact same thing, but it's a minus instead of a plus. So again, same thing, but minus instead of a plus. And now the second one is the J component. J component is a vertical one, so N is the positive N, so that's going to be, just put N like that. So N like that, and now we're going to have to subtract these two, the W and H components. So minus, the W is going to be cosine, so mg cosine theta, and then the next one is going to be minus the H max, and this is going to be sine theta. So the sine theta angle's on the other side, so it's going to be the opposite side, and that's going to be negative and negative, yeah, so this equals to 0. So in other words, we're going to get mg, I'll put h max first, so h max sine theta, and then plus, because we move this both to the other side and solve for n, it's going to be mg cosine theta, this equals to n. So just to get rid of all the negatives, is that, this is equation 2. And this is in fact the exact same thing as part C, because in this case, F is not included. The vertical component, F has no vertical component. So H max sine theta plus mg cosine theta equals n. Same thing, except instead of H min, we have H max. So we go back up here. This is equation 2. H min sine theta plus mg cosine theta equals n. Now we have H max. H max sine theta, mg cosine theta, and n, like that. And likewise, again, we put the n inside equation 1 and then solve for it. So we go put this inside and then solve for it here. And what we end up having is, so thus, we're going to have H max cosine theta minus mu sub S, and then this is the n, is going to be this right here, H max sine theta plus mg cosine theta, and this equals to, yeah, that's this part right here equals mg sine theta. This is just our n. And this is going to equal to mg sine theta. Alright, so same thing, we're going to start solving for all of this, and this is going to be, just simplify this all further, h max like this. So what I'll do is I'm going to factor out the h max right here, h max multiply this u sub s inside, so h max is going to equal to cosine theta minus mu sub s sine theta. And then the next one, this one, I'm going to multiply that inside and move it over to the other side. It's going to equal to mg, and also factor out the mg right there. So we're going to mg sine theta. And then this is going to be plus. Now this one, because this is mu sub s times mg cosine theta, that's going to be negative, but it's going to be moved over to the other side, it's going to be positive. So it's going to be mu sub s cosine theta. Like that. And then likewise, this is going to be equals to h max. Just divide this out. We're going to get mg, and now we're going to get a sine theta plus mu sub s cosine theta all over cosine theta minus mu sub s sine theta. And now this is going to be times it by, again, divided by 1 over cosine, 1 over cosine theta, 1 over cosine theta. And then what we end up having is, this equals to, well, mg, and then this is going to be sine theta divided by cosine, that's just going to be tan theta, and then plus mu sub s, and cosine cancels out. And put this bracket, now the next one is going to be cosine divided by cosine is 1, and then minus mu sub s tan theta. And then also, we just replaced mu sub s with tan theta s. So this equals to mg tan theta plus, again, same thing as before, tan theta s, because it's at the friction force is at a maximum, so the mu s is at a maximum. So 1 minus tan theta s tan theta, like that. All right, and again, this is the exact same trig identity as above. Actually, it's the reverse side. So this is tan theta plus tan theta s. This is 1 minus tan theta s times tan theta. So we go back to our trig identity. Now we have this theta. This is x is plus on the top, minus at the bottom. The other one had a minus on top, plus at the bottom. Exact same thing, x, y, or theta, theta s. Theta, theta s. So it has to be plus. So this is going to equal to tan theta plus theta s. So equals to, and this is equal to tan, just mg tan theta plus theta s, like that. This is h max, like this. Alright, so this is what we have. Box this all out. There it is. And this is exactly what we were asked to solve. The other one was a minus, this now is a plus for the, okay, this, I just don't know why my OneNote glitches out sometimes. So there it is, mg tan theta plus theta s. Let's go scroll all the way back up. And alright, so there it is. H max equals mg tan theta plus theta s, and exactly the same. The other one's minus. This is going to be a plus. And now, last thing we're asked is, does this equation seem reasonable? Explain. So basically, same thing as before. Now we've got to explain it. And yeah, let's see what I wrote down / what the solution manual had written down. Let's erase this. Alright, so we would expect H max to increase as theta increases. So as it goes up, we're going to need a bigger, more and more steep one. So as it goes steep like this, we need a very big force right here to keep it from stationary. Otherwise, you're going to have the weight of gravity is going to be pushing it very, very hard downwards. And because the friction force is already max. So then, we can't keep increasing it. So it's going to be pushing it really, really high up. We would expect H max increase as theta increases, with similar behavior as we established for H min, but with H max values larger than H minimum, because now we have this theta plus theta s, and also because we expect it to be increasing as well higher, or the values of it has to be actually greater than before because we had a minus, but also we know that the tan goes up like this, and each time if you get further out to the right, it's going to go up higher than that. So it's going to be a larger value, so that's reasonable. So we can see this is the case if we graph h max as a function of theta, as the curve is the graph of h min translated to theta to the left. So the equation does seem reasonable. And you can see this by, well, if we just graph it out. So what I'm going to do is I'm going to graph like this. I'm going to call this tan of, just tan of, actually let's put y right here. It depends on the function. So this is going to be theta. And now just look at the positive side right here. I'll make it like this. So it's going to go up like this. This is at 90 degrees. This is at 90 degrees right here. Is that theta is equal to 90 degrees. So if we have just an angle right here, or instead of a line like that, I'll just erase this. All right. So yeah, let's just say we had this right here. All right. Yeah. Let's say we had okay, it goes like this. This is our theta. Okay, this is I don't know why it keeps shifting. This is our theta. All right, here I just fix that up. So let's say that's our theta, and let's just exaggerate. We have over here, between here and here is theta s. So then this is going to be right here is theta plus theta s. And then the other one is going to be theta from here to here is also theta s. So right here is going to be theta minus theta s. Yeah, so in other words, this right here, so for every theta, this tan theta plus theta s is going to be exactly the minimum, so h min, but shifted to the left by 2s. So in other words, at this point, if this theta minus theta s, we're supposed to have here. So this is going to be like shifted across there. And so what I'll do is I'll just paste this one here. I'm going to copy and paste it. All right, so let's just move this over. Okay, so if I move this over here, yes, move it over like this. Yeah, so basically just move it exactly to theta s. This is 2 theta s. So all it is, basically whatever value we have here for h min, the h max is going to be the same thing but shifted over twice. So this is going to be higher than it at all times. So that it does seem reasonable there. So we can see this is the case if we graph h max as a function of theta, as the graph is the graph of h min translated to theta s to the left. So the equation does seem reasonable because h max needs to be higher than the h min now, because we also have the friction force going opposite. So we could even increase it even larger, whereas the other one, the friction force on the opposite side, going upwards. So that h min doesn't need to be as high, but now h max, the friction force is aiming at us, so we need to be higher to overcome it, and so on. So we have a large max we can achieve. And notice that the equation predicts h max goes to infinity as theta goes to 90 minus s. In other words, when this goes to theta plus theta s, yeah. So if we have 90 minus s right here. This becomes 90 minus theta s plus theta s. This is the theta. Yeah, just fix that up. So 90 minus s as this approaches this one, and then this 90, these cancels out. So in other words, it's approaching 90 right there. So as this approaches 90 minus s almost vertically, this is going to infinity there. In fact, as h max increases, the normal force increases as well. Yeah, so as you're increasing the h max, so for example, if you have the block right here, and as you're going to this much, increasing it, the normal force also increasing it as much as well. But when the theta is between 90 minus s, minus than or equal to, and less than 90 degrees or equal to. Yeah, and in these cases, the horizontal force is completely counteracted by the sum of the normal and friction forces, so no part of the horizontal force contributes to moving the block up the plane, no matter how large its magnitude. All right, so now if I graph this out, just be making a bit more sense. I'll just visualize what this all means. So let's say we're going to have multiple angles. We're going to have the first one's 90 degrees. So there's 90 degrees that right-hand side. The next one right here is going to be, let's say we had theta s. This is for where the friction becomes maximum. Theta s. And now we have another one which is 90 minus theta s. I'm going to make this I'll make it a bit flatter. So this is, let's say, above it, friction is going to be just maximum. And now this is going to be theta s like that. And so in other words, this part right here, this is going to be at theta. So this from here to here is theta. This is going to be 90 degrees minus theta s. 90 degrees minus theta s. Yeah, so above this theta minus theta s and below the 90 degrees, what we end up having is it does not matter. So the equation predicts that it does not matter how hard the horizontal force is, it will never go up. This will be counteracted by the friction force, just the maximum friction force, and the normal force, because the normal force is constantly increasing as well. So you're going to have a period where, so if you have the block like this, so it does not matter what you apply to this at when it's above this, equal to or above. This is h like here. So this goes to infinity. And this, again, the absolute value is going to go to infinity. And this is going to be normal, because normal force is going to be increasing as well as you're applying to it. It's just a reaction force. And this is the friction force F. So then, again, for 90 degrees minus theta s, where the angle's between it and 90 degrees, you're going to have h, I'll just go magnitude of h naught, or h vector, equals to h max, approaches infinity, and block doesn't move. Doesn't move. So that is what this predicts. That's pretty reasonable, I think, because as it goes higher up, you're not going to go up higher and higher because the reaction force is increasing as well, and they always have this friction force is already maxed out way above this. So when it's really, really steep, it does not matter how hard you push it, you're going to be counteracted by the normal force and the friction force at all times. Because again, if this is going to infinity, even the normal force is going to infinity. So you're going to have some reactionary force component that's horizontal of the normal force that's approaching infinity as well. So it does not move. That's quite fascinating stuff there. So yes, epic stuff. All right, and now let's take a look at problem 8, and this one is about finding the volume of a solid from its shadow. So yes, it could be quite an interesting problem here. So a solid has the following properties. When illuminated by rays parallel to the z-axis, its shadow is a circular disk. And if the rays are parallel to the y-axis, its shadow is a square. And if the rays are parallel to the x-axis, its shadow is an isosceles triangle. So it's basically going from the top, you're going to have a circle. From the side, you're going to have a square. And then from the x-axis, so going into the page like that, you're going to have a triangle. So now the question is, what shape is it? That's quite fascinating. All right, in exercise 44 in section 12.1 of my calculus book, you were asked to describe and sketch an example of such a solid, but there are many such solids, and I didn't actually do a video on this, but there are many such solids, so in this case, we're going to pick one that has a specific length. So assume the projection onto these xz plane is a square whose sides have length 1. All right, and here's the question here, just copy and paste it from my calculus book. So again, describe and sketch a solid with the following properties, and so on. Illuminated parallel is a circle, on the z-axis circle, y-axis square, and x-axis isosceles triangle. All right, so we're going to assume that the xz plane is a square whose sides have length 1. So then we can find a specific shape like this. So part A, what is the volume of the largest such solid? So instead of just any one of them, we're going to pick the largest solid. And part B, is there a smallest volume? All right, so let's take a look at part A first. So solution to A, let's first draw our shadows just to illustrate this. Yeah, so let's draw this out. So let's draw our Z. This is our Y, this is our Z, and this is our x-axis like here. X-axis like that. And let's say we are going downward parallel to the Z-axis or up. But let's just go downwards right here. So if we go down on this object, we're going to get a circle shadow like this. All right. And now if we go parallel to the y-axis, So let's go from here to here. We're shining light from there. We're going to get a square. The square like this. And yeah, we're going to get a square like that. And if we go parallel to the x-axis, we'll make it a bit better. Like this, we're going to get an isosceles triangle. Like this. And yeah, you could shade this in. Alright, and since we're asked to find the largest such solid, so we have this shape, and so the largest possible solid with these shadows is achieved by starting with a cylinder with a circular cylinder of diameter 1 with axis, the z-axis, and with a height of 1. Yeah, or with the axis being the z-axis and with a height of 1. And this is the largest solid that creates a square shadow with a side length 1 in the y direction and a circular disk shadow in the z direction. And to draw this for convenience, we place the base of the cylinder on the xy plane so that it intersects the x and y axes at plus or minus 1/2. So in other words, what I'll draw is let's draw this solid. So we start off with the largest solid. Just first off, start off like this. So here is our z, and now we're gonna have a circular cylinder like this, and it's gonna go down like this. So then the base is at the origin, and let's go all the way down across here. It goes down to the origin. This goes around like this. Okay, this goes like that. And then this is the y. This is the x. And now this is around like that. So that goes around like that. And we're given that the height is 1, so it makes a square. The height is 1. So at this top part, it's 1. And then this is 1 because we're putting it at the origin in the center. So it's 1/2. This is going to be 1/2. And then backwards going to go etc. Accordingly, but anyways, that's a bit of interesting shape. I didn't draw it exactly perfectly, but anyways, so if you shine a light on it this way from the y-axis, I'll draw I didn't draw the y-axis perfectly on it, so we'll just go y-axis like this. We're going to get a square shadow. This is a perfectly from looking at it from one side, all you see is this. All you see is a square. So you're going to get a square shadow. Like this. So it's square shadow height of 1, 1. So we're going to basically, projection on the XZ plane is a square whose side lengths have 1. Yeah, so in other words, the X and Z plane, you're going to get 1 right here. So this is 1, 1, 1, 1, like that. So just a perfect square. 1. I'll just go, you could do that. We could just do all of them. It's just a square. So that's what we have. And also going downwards, we have a circle. So if you point down here, well, it's a circle, and well, it's a cylinder. So you're obviously going to get a circle underneath there. Like that. Shadow, like that. All right, and then we then remove as little as possible from the solid that leaves an isosceles triangle shadow in the x direction. So we want to make a triangle on this side right here. So this is achieved by cutting the solid with planes parallel to the x-axis that intersects the z-axis at 1 and the y-axis at plus or minus negative 1/2, as in the figure below. Yeah, so in other words, what we want is, so here's our shape. Let's just draw, this is our cylinder. So what we want to do is cut this, and I'll use a different color. I'll draw this in red. So let's say we have a red plane like this. We're going to cut it, that cuts straight through at the edges like that. And it's going to be this on the other side. And this goes all the way also at the bottom there. Like this. So then we're going to cut that and then basically remove all of this extra piece there. So what we end up having is, I'll close this. We get a shape that looks like this. It looks like a wedge. So it's going to be like this. And I'll draw it like this. It's going to be cut off, sliced off all the way. And here you're going to be slicing off less than the top one. You're going to have sliced off bigger edge there. And then it goes, and then this part's going to be just like this, sideways. So you're looking at a 3D. and this is going to be in a circular setup there, like this. So it's going to look something like this shape, or I'll make it a bit more like that. Or here I just fix that up. So this basically, we cut it, turns out like this, and this is our z-axis like that, and this goes down, etc., all the way in there somewhere, and like this. And then again, not to scale. I'll use the solution manual photo soon just to make it a bit better. And that, and this is going to be, this is the y-axis, like this is 1/2. So that when you're shining light this way, parallel to the x-axis, you're going to get a triangle. Looks like a triangle in the back, an isosceles triangle. Shadow there. Here, I just made it a bit bigger, so makes it just in the back like this. Alright, and here is the solid. I just copy and paste from the solution manual here, so it looks much better than my drawing, and it's taller, and so on. Except, except my drawing might have it a bit more to scale, because this one's going to be it looks a bit taller than it is thinner, but anyways, yes, it might be a rectangle on the other side here. Looks like a rectangle shape, but anyways, just imagine it being a square. So to compute the volume of this solid, we can take vertical slices parallel to the XZ plane. So if we were to cut this all up like this, and cut it up all the way across there, and so on, and what we end up having is a shape or a bunch of slices like this. And basically, we're going to calculate each volume of each slice infinitely small, and then sum it up using an integral. Alright, then going further, so the equation of the base of the solid is the circle with radius 1/2. So basically, the bottom is just a circle. Yeah, just the radius is just is 1/2 or 0.5. So we can use that. So thus we can obtain the length of the cross. The length of a cross section. So we can know the length of it because we know the equation. Yeah, so we can find out the length of it, then take an infinitely small section here. We can determine the length using just the equation of a circle, and then so that's we can obtain the length of the cross section of the solid to the right of the origin. So we'll look at to the right of it. We'll look at this semicircle segment over there. And then from here, we also know the height of this. We can also calculate the height of this. This is just going to be as a function because it'd be a horizontal. If you look at it from this way, this is z, this is the y. You can find an equation. This is just a straight up line there. So you can find an equation of z in terms of y. So we'll see how this all plays out. And yeah, I wrote that right here. So we can also obtain the height as a function of y, and thus the area of the cross section. Alright, so the equation of a circle, let's take a look at the xy circle. So x plus x squared plus y squared is going to equal to the radius. And we know the radius here, so we're going to just graph this circle right here. That's xy plane, and then the radius is 1/2. So it's going to be 1/2 squared. So in other words, this equals to 1/4. Alright, so we have this equation, but what we want to deal with is, well, we'll just make this as a function of y. So what I'm going to do is write this as, because we're going to be graphing it on this side. So on to the right of the origin. So so that's going to be on the positive y-axis. So what I'm going to do is I'm going to rearrange this so that x, so just solve for x. So x is going to equal to plus or minus, and then move this over to the other side and then square it all. It's going to be square root. Yeah, I mean square root also 1/4 minus y squared, and we only want to deal with just a positive for now. So we're only dealing with a positive value. So we'll just make it positive like this. So x is like this plus, and this is 4. I'll just leave the plus like that. Or actually, I'll keep the plus in there just so we'll keep the plus in there just so that we're dealing with one side of it for everything positive. This is going to be 4y is less than or equal to 1/2, and this is going to be greater than or equal to or 0. From 0 all the way to 1/2, and that's because when you put 1/2, you're going to get 0. And when you put in when you put y as 1/2, it goes to 0. And if you put it more than 1/2, you're going to get a negative value. In other words, we're going to be dealing with imaginary numbers. And if you put this y, if you have it less than 0, you're going to have another scenario. This is going to be positive. It's going to be the same thing as this. You're not going to have a one-to-one function. So again, I just mouthful there. So let's just graph this out. All right, so I'm going to graph this out actually in 3D, just so it makes more. Actually, yeah, I'll graph it out in 3D. or instead of 3D, I'll just do it like this. I'll put the x positive here. This is the y positive, just so that this lines up with this right there. And then what we'll have is when y is 0, so when y is 0, we're just going to get 1 over square root 1 over 4. So in other words, we're going to get 2, 1 over 2. So this is at 1 over 2 right here. This is 1 over 2 is at 0. And then when y is 1/2, x is 0. So in other words, it goes like this. So we're only going to graph from here to here. And we're not going to deal with the scenario of negative, because otherwise it's going to go over to this side. We won't have a one-to-one function. No, actually, this won't be a one-to-one function either way. Never mind. So, but nonetheless, the solution manual does it with this way, so that we'll have it just from here to here. And what we can do instead is it's going to be exactly a mirror image. So we just multiply by 2 when we take out the full when you calculate the full length. When you get the full length there, we just multiply by 2. Like that. So on this side. So we're just dealing with the right of the origin, and then we can multiply the full volume by 2 once we do it all. So we're only dealing with the positive side right here. And we also know that we could turn z as a function of the height as a function of y. And we'll draw this right here. So if you look at it from this side, it's a triangle on that other side. So we'll look at the z. So we're going to graph out, I'm going to graph out z like this. Alright, so z like this, and there's the y, and it's going to be an isosceles triangle like this. So this is the height 1, this goes to 1/2 there, this is z, this is y, and this is going to be our 1. So 1, and remember it goes over to there to another 1/2 over there. So that is our height there, and so then we can calculate each length right here. So this length right here is going to be, we'll call this, well, first I'll call this is going to be a rise or a run. So it's going to rise by 1 and run by 1/2. So then the slope is just going to be, the equation of the line is just going to be, well, z is equal to the origin, or the initial point, 1, minus, and then it's just going to be y times rise or run. So rise is 1 and divided by 1/2, like this, y. And we're minusing because we're going downwards. So then this goes on top. The 2 goes on top. We're just going to have 1 over 2y, like this. Yeah, so thus what we end up having is, so what I'll do now is I'll draw out a section of it. So we'll take out just a general section. This is going to be our x. This is going to be our z. And it's going to go, we're going to take a slice here. So I will highlight a slice right here. Yeah, so let's just take this slice, for example, and just take that out. So let's say we take it out and we only look at that one, and let's say it's infinitely small thickness. So that means we're going to have a slice like this, and it's going to go at an angle down like this. But it's infinitely small, so this angle doesn't really matter. And it's going to be like this. So there is our infinitely small height, and this is going to go, I'll draw this fully like this. And this y goes through it like that. And this is our y, and I'll move this over. And now here I just quickly fix up how the box looks like, because I had it actually below the as xy plane. So I'm going to make it just on top like that. This is going to be our y, like here. And let's say the 1/2 is all the way here. This is 1/2. And the height is all the way up top here. Actually, we don't have to extend this anymore, because this is going to be a function of z. A function of y anyways. This is just the points we're going to be taking the integral from. It's from 0 to 1/2. And now this is the infinitely small thickness dy. So it's in the direction of d. And now this full width right here. This right here is just 2 times this right here. Yeah, so in other words, if I draw the bottom like this, I'll draw it that's hitting this part right here. So this is our a quarter circle. That's this right here. Here, just fix that up. So that's our quarter circle. I'll just highlight it as well, like that. So, and then the distance from here to here is just x. So this is our x. So then, in other words, this is another x, absolute value sign of x, like that, on that side, just so that, we'll just put an x and x, like that, because we're only looking at the positive one, and then the other one is going to be x value as well. So in other words, this is going to be 2x, which equals to this right here, 2 times square root 1 over 4. Yeah, 2 times. Let's put this again. 2 times square root 1 over 4 minus y squared. Like that. So that's that. And now the height of this is, well, we know that's just the height is just the z value at whatever y value that is. So in other words, this height is going to equal 2. Z equals 2. 1 minus 2y. 1 minus 2y. So there it is. That's what we have. All right, I just moved it up there. And now this whole cross-section right here, this has an area of, and I'll put an area like this. This area, this cross-section, we'll call it a of y. I guess erase this. Let's move it like, okay, so this is going to be a of y. Yeah, here, just fix that up. So a of y, and this area is just going to be equal to, well, the height times it by the width. So in other words, or the width times by the height. So the width is 2 times square root 1 over 4 minus y squared. And now the height is going to be, well, multiply this all by 1 minus 2y, like that. All right, so we can, yeah, so that's our height. I'll just leave it like this. Actually, I'll box this area, and this is our area. All right, so we can now solve, we'll now solve the volume of the solid by taking an integral and multiplying by 2 because of symmetry, because right now we're only taking from 0 to 1/2. So in other words, we're only finding the volume of the right side, so we just multiply by 2 to get the total side. So thus what we have is volume, called V, this equals to 2 times the integral from 0 to 1/2, and this is going to be now this area, A of y times it by the infinitely small thickness dy. So dy we get a small slice, and then just sum it up using integrals. So this is going to equal 2 times, and now the integral from 0 to 1/2, and now put this whole thing 2 square root 1 over 4 minus y squared, and now we have a 1 minus 2y for the z, and this is dy. Alright, so now we could multiply this inside, so we'll have 2 integrals. So this ends up equaling 2. So 2 times 2 right here is going to be just a 4. So 4 times it by the integral from 0 to 1/2, and this one's multiplied by 1, so that's just by itself. So square root 1 over 4 minus y squared dy. And now this one multiplied by, in this negative 2y. So that's going to be, now this is going to be 2. And there's going to be another negative 2, so we're just going to have a negative. Yeah, it's a negative 4, 2 times, so this 2 times it by this 4. Well, actually, we'll have a 2 times 2 and then another 2, so it's actually 8. So this is going to be 8, like that. Yeah, so 8, and this is going to be, it's negative, and then there's a y there. So we're going to take the integral from 0 to 1/2 of y square root 1 over 4 minus y squared dy. So we have multiple things like that. All right, so let's solve these each separately. I'm going to call this 1, each of these integral 1, so I'll call this 1, and this one right here, I'll call this 2. This one 2. So the first one right here, this is just a semicircle. Yeah, this is just a circle, a quarter circle actually. The square root 1 over 4 minus y squared. That's exactly what we had here. So in other words, this is a quarter circle. This one is, again, this is x equals square root 1 over 4 minus y squared. So that's just a quarter circle. So I'll just write this as, yeah, so 1. This is just going to be the volume right here. V of 1, this equals to, well, quarter circle. 4 times 1 quarter circle. 1 quarter, and then this is a circle. And the radius is just 1/2, because again, that's 1 over 4. This was exactly this one. So that's just 1/2 radius. So in other words, quarter circle of I'll put quarter circle like that. Then this equals to 4 times it by 1 over 4, and the 4's cancel. So we're just cancel like this. And this area is, again, a circle is just pi r squared, and where r is just equal to 1/2. So that's just going to be 1/2 squared. In other words, we're going to get, well, 1 over 4. Let's put a full follow along just to put it all in. Okay, this is going to be pi times it by 1/2 squared. So this equals to pi over 4. like that. So that is our first volume. So now the second volume, I'll call that 2. Alright, this is just like that. Yeah, so the 2, 1, so we got that volume, so I'll call this V sub 2. And this one here is going to be the 8 there, so I'll just go, this equals 2. And yeah, so this one is an 8, and I'll just write this whole thing out because we're going to actually use substitution. So 0 to 1/2 y square root 1 over 4 minus y squared dy. So what we notice here is this looks complicated because we have this y and the outside, there's another one there. But if we have this 1 over 4 minus y squared, if you take the integral of that, this becomes this y squared, this vanishes, this y squared will go to 2y dy. So in other words, what I'm going to do is I'm going to let, and then we can see some cancellations going on. So let u, so we'll use substitution, u equals to 1 over 4 minus y squared. So the reason for this is if we take the du, the derivative, this equals to, well, 1 over 4 vanishes, that's just 0. Now this negative 2 squared is going to be negative, negative y squared is going to be negative, put the 2 down, y, it just has 1 by itself, and then integral, the derivative of y is dy. Like that. So notice what we have is this du replaces dy and y, and this is also, there's an 8 there. So v2, they put the 8 there as well, and this also replaces, again, there's another 2 there, this becomes 4. Yeah, so there's the y dy, there's this part right here, and then we just have to make it into a negative. Alright, so this becomes, so then if we plug this inside, we get, put this, we're going to get v2 is equal to, 8 is going to cancel with this, so we're just left with a 4. So we're going to have a 4 integral of from 0, or we don't need to put the, I'll just ignore that right now. Actually, I'll keep it in, but I'll put a y equal. So we're going from y, not du. We'll replace it afterwards once we get it all. So from y equals 0 to y equals to 1/2, because we're changing the variable right now. So then this y and dy, and there's a negative now, and there's also a negative sign now. Put this negative here, so negative 4, and now the y dy is just turned into a du. So we're just going to have a square root u, because we replaced the u, this 1 over 4 minus y squared, and then du. So replace it all. So now this is just a basic integral right here. All right, so this equals 2, and this equals to just negative 4, and then let's take integral of u, square root u is just going to be, well, add a power to it, so add 2 over 2, because that's 1 over 2. That becomes u 3 over 2. And then put a 2 over 3 like this, so that when you, it's the antiderivative, you take the derivative, 3 over 2 cancels with this, and then subtract the power, so we're just going to get square root u. So that's that, and yeah, so then this is integral from y equals to 0 to y equals 1/2. Alright, so now we could plug this back in. So let's just plug in our y again. So it's going to be negative 4, and this is going to be 2 over 3 times it by u is going to be, well, 1 over 4 minus y squared, and then to the power of 3 over 2, and this is from 0, this is from y equals 0, and now we change the variable back to y, so we don't need to write y equals 0, etc. That's obvious. So this is going to be 1 over 2. Alright, and now we can start evaluating this. So this is going to equal 2, and I'll just take out this 2. This is going to be negative 8 over 3, so move the 2 out, and a 3. So negative 8 over 3, and now this is going to be a giant equation. So when you plug in 1/2 inside, so when you plug this 1/2 inside there, this just vanishes actually. So 1 over 4 minus 1 over 4 is 0, so that's just 0. So in other words, we get 1 over 4 minus 1 over 4, so that's 0. And now we subtract, now we put a 0 inside there. So that's going to vanish. We're just going to be left with a 1 over 4 to the power of 3 over 2. Like that. Alright, so let's see what ends up happening. Let's simplify this. This equals to negative 8 over 3. And this is going to be 1 over, this is going to be, let's times this by, so there's a negative times it by a negative, it cancels to be positive. And now we have 1 over 4, like this, 1 over 4, so times it by 1 over 4, and this is going to be square root, yes, 3 over 2. So this is looks like an interesting problem right here. This is the same thing as writing this part right here. This just equals to, I'll put this as the same thing as writing 1 over 4 power 1/2 and then to power of 3. So in other words, this becomes 1 over 2, so square root of 4 is 2. Well, actually, before even doing that, we don't really need to do that part. We can just look at this 8 right there, and just rewrite the 8 as a 4. So this equals to 2 times 4. And in other words, 4 is just 1 over 1. And I'll also put a 2 over 2 right here. So that's the top part. This is 3 times 4, 3 over 2. Now we can just subtract the power. So this is going to be, so we can subtract 4, 2 over 2. So this is bigger, so we'll subtract it from the top. So this one subtract or this one subtract into this one. So we get a 2. And this just vanishes. We're going to get 3 times 4 times, 4. And then this is 1 over 2. So 3 over 2 minus 2 over 2 is 1 over 2. And this one now is equals to 2. So this equals 2 over, 3 times 2. Square root 4 is 2. And this cancels. We're really left with 1 over 3. So that's entire integral equals 1 over 3. So yes, epic stuff there. All right. So thus, what we have is, volume equals to V1 plus V2, and this equals to, this equals to just the integral. I'll just put the whole thing out. It's equal to 2 times integral. 2 times integral from 0 to 1/2 a y dy, and this equals 2. And here is rearrange our order, so let's put this instead. So 2 times square root, integral from 0 to 1/2 a y dy equals v1 plus v2, and this equals 2. So what is the first equation? Pi over 4. So pi over 4 minus 1 over 3. So this is our volume of the solid, of the largest solid that has those 3 shadows. Epic stuff there. And also, lastly, I just want to add one more. So if you plug this into the calculator, you're going to get roughly 0.45. So in other words, V of the solid is roughly equal to 0.45. So that's epic stuff there. So remember, it's pretty much, if you take a cylinder that has a height 1 and has a radius of 1/2 and so on, you're going to end up, and then remove all the pieces to get it a isosceles triangle. You get it like this. So it's pretty epic stuff. And this makes sense because if you take a look at the square, so that is a square on this other axis. So if you look at it from this axis, here's a square, but it's all sides 1. So this is all just 1. So in other words, a full solid that has 1 thickness, if you had it in 3D, that's just going to be 1 times 1 times 1. So in other words, just 1. So 0.45 of it. So you shave off 55% of it. So that's 55% of the solid to get its volume. Of its volume to get this 0.45, roughly there. All right, and now let's do a quick calculation check. And you could use the integral-calculator.com website. You just plug it in. So in our case, we have 4 squared. You can just type in 4 squared, 1 over 4 minus y squared, and then you get, it automatically presents it in this format. So 4 times 1 over 4, all squared, square root there, minus y squared dy. And you could change a variable, add the integral from 0 to 1/2. So you get this giant equation. This one, we just did a circle, so we didn't have to do any sort of other stuff there. So we know it's a circle, a quarter circle, so we just multiply it by pi r squared. And divided by 4, we cancel those out, we just get pi over 4. But if you use the integral calculator, you get this giant thing with the arc sign and so on. And eventually you can plug it in, and this automatically solves it. This is the indefinite integral. This is a definite one from 0 to 1/2, and that's just pi over 4. That's exactly what we got. And we just bypass it using our brain. It's epic stuff. And this other one, here's another one. You can also share the URL. So this one is for the second one. So this is a V2. This is from 0 to 1/2. You could just write literally 8y. Then you put a multiply sign there. 8y sqrt for square root. 1 over 4 minus y squared, and automatically knows what you're talking about, and automatically generates this format, 8y, and then square root 1 over 4 minus y squared dy, and you get basically this right here, and exactly what we had, 1 over 4, 8 times 1 over 4 minus y squared, and then all to the power of 3 over 2, and there's 8 over 3. There's exactly what we had over here. here 2 over 3, 1 over 4, and this can be 8 inside there. 1 over 4 minus y squared divided to the power of 3 over 2. Then evaluates for you and you get pi over 4. Oh no, that's the other one. Whoops. You evaluates for you and you get 1 over 3. Exactly what we had. And basically now if you go pi over 4 minus 1 over 3 using my built-in OneNote calculator, you can just go and solve it. Press space, automatically gets you 0.4520, etc. So we just rounded up to 0.45. So epic stuff there. All right, and now let's just jump over to part B. All right, so part B, we're asked, is there a smallest volume? So just to recap, in part A, we found the largest volume of a solid that has the shadows that form a circle, a square, and an isosceles triangle on their respective axis, where the square has a side length 1. So, but to find the smallest volume, well, we could keep removing from the solid infinitely small, just keep going on and on as long as the skeleton of the shape is formed. So as long as we have our square, isosceles, triangle, and circle. So technically we don't need an actual volume. We could just keep shaving away. So we could take this material and keep shaving away it until we have all we're left with is a thin, a tiny thin, like almost zero volume square, and then a triangle that has then a triangle in the center, and then a triangle in the center here. Let's draw this better. Yeah, whoops. Yeah, just a triangle like this in the center, isosceles triangle, and also the circle, as long as you have a circle at the bottom. So you could basically remove it all until you have a tiny, super thin, super thin material, zero volume. So there is actually no lowest volume. So going further here to solution to part B. So there is not a smallest volume, and we can remove portions of the solid from part A to create smaller and smaller volumes as long as we leave the quote skeleton shown in the figure intact, which has no volume at all and is not a solid. Thus we can create solids with arbitrarily small volumes. So yes, basically as long as we have the skeleton there, so we can have basically any amount of material on it. Just any kind of thickness as long as it's super small. And we can just do arbitrarily small. It can go even smaller and smaller. So there's no smallest volume. So this is basically the skeleton of it. So imagine you remove all this material. All you're left with is this right here. So we have a thin square there. So we have a thin square. And then on this axis, on the y-axis, on the YZ plane, we have a isosceles triangle like there. Then at the bottom, at the base, we have a circle. Yeah, so we have a circle. And again, these are super infinitely small, so it's zero volume. So as long as you have any sort of thickness, and you can go arbitrarily small, so there is no smallest volume. We can keep it going smaller and smaller and smaller, approaching zero. And again, if you flash a light, illuminate light on the bottom like this from the z-axis parallel, you get the circle. You get a circle shadow. Going this way, you get an isosceles triangle. And then going this way or the other way, you get a square. So yes, fascinating stuff there. And that is actually all for problem 8 and the entire problems plus. So another giant long video. And hopefully you enjoyed this epic long video. So I'm going to start just scrolling up as I usually do and start blabbing about random stuff. So anyways, hopefully you enjoyed this epic long video. And again, I'll be breaking down every problem into separate videos and putting that into the sections playlist. And all the links will be in the description and so on, as well as on mes.fm/links. Just going to keep scrolling up. Okay, something's freezing. There we are. We just teleported. So I'm just going to scroll all the way up. And again, all the notes in PDF format and in article format on the Hive blockchain. The links below. And that is all for today. Let's scroll back up. But anyways, so that's all for today, guys. And there's links to everything else. And thanks for watching. And stay tuned for another math easy solution.